Okay, well, I'm looking through the different pictures. I recognize some of you, so I know you've been in the STEM classes here at JUMP before. Welcome back. It's nice to see familiar faces. My name is Shannon Egley, if you don't know who I am. My job at JUMP Simulation Training and Education Center is anatomical coordinator, and this is actually the anatomical lab in the background. So the anatomical lab is also known as a surgical lab. Some people call it cadaver lab. The reason that we call it that is because we don't do a lot of just basic anatomy dissections like we're going to do today. We do a lot of work in surgical simulations. So we work with cadavers, which are people that have passed away and they donated their body to science. And then we bring them in and we set up a surgical scenario, kind of like on the surgical table right here with the surgical lights and surgeons surrounding it. And the surgeons practice surgeries that they would do on the living people. And the nice thing is that they don't make a mistake. Well, I shouldn't say that. They do make mistakes, and they don't hurt anybody by making those mistakes. So my job is setting up and preparing and making sure that the lab goes off the way it's supposed to, and helping with the curriculum, which is the teaching material, and building everything, and holding and hosting for those surgeons to come over. So it's really nice because a surgeon, when they're going to medical school, they don't actually do a lot of surgeries during medical school. So once they're a practicing doctor, is the first time they really get a chance to do surgeries. And how would you feel if you went to a doctor and it was the first time they'd ever done a surgery before and they're going to cut into you? I would be a little bit nervous. So they come in here, we set up the surgical scenario, we make them act exactly like it is in a real surgery, and then they get practice over and over again until they're very, very, very good at it, so they don't make mistakes in the real life situation. But the whole center, JUMP Simulation, is a medical simulation building. So we imitate doctors' offices or surgical suites or any kind of medical scenario. We have, if you've been here, you've seen the big ambulance in the bay full of cameras. So we can teach paramedics, nurses, technicians, surgeons, general practitioners, everybody all the way up the line. And like I said, my job here is anatomical coordinator, so I set up the anatomy stuff in this lab. My other job is at the University of Illinois College of Medicine. I think, oops, wrong side, that side. Here in Peoria, I'm a clinical associate of anatomy, so I teach medical students their anatomy, which is kind of nice because I get to work with the medical students while they're becoming doctors and learning their anatomy, and then once they become a doctor and they're ready for the surgery stage, I work with them again over here. So it's a lot of fun getting a chance to work with them all through their careers. And hopefully, I think you are the high school group, so everybody in here is in high school. You're starting to think about what you're going to do when you go to college and where you're going to do after college. So like me, for instance, I didn't go to college until I was 30, which was not a great idea, but I did try a lot of things I didn't want to do for the rest of my life. And then when I went to school, I focused on psychology because I liked the way that people thought. And then when I got accepted to the med school I went to, I wanted to be, I wanted to be in neurosurgery, and started thinking about the pathway. And I thought, well, I think I want to do psychology. So I wanted to be a psychiatrist. And then I actually shadowed a psychiatrist for a while and decided it was not for me. So I thought, well, neuro is the way to go. And I really enjoyed research and I enjoyed being a scientist. So instead of going to neurosurgery or neurology, I ended up going to neuroscience and doing research. So now's the time that you start thinking about what you want to do, but also know that you're going to probably change your path a lot of times. You could be a basket weaver in college and get a degree in basket weaving and still go on to med school and be a doctor. But hopefully you're interested in sciences, and this will spark you a little bit more. And the first step at any science is learning the anatomy. And it's just like going to kindergarten and learning how to write an A or a B or a C or D. That's the anatomy. And so today we're going to do the anatomy of a shark and compare it to a human, because you're not quite old enough to come spend time in shadow in the lab with me and actually work on humans. So this is the next best thing, kind of. All right. So I'm going to flip back to the camera that's looking down. If we need to see me for some reason, I'll come back, but I don't like looking at myself in that image, so we'll go the other way. I'm not super fast at switching the technology, so it might take me just a second. Uh-oh. There we go. Did it work? Did not work. Now I've done it. I've broken things. Maybe that's better. Maybe not. Right. I always have a backup. Okay, hopefully you can hear me. Give me a thumbs up if you can hear me. Awesome, perfect. So you got a kit you picked up, and we'll walk through that. Put it all together. You got a plastic bag that looks just like this. I'm not sure why the image isn't working. Is it frozen for you too? Can you see my hand in the screen? Oh no, technology. Can you hear me now? Can you see a picture of jump? Can you see a thumb up? Oh, it's a miracle. Okay, so you got a bag like this with a shark, probably in a box, and it looks like all this mess inside. Except you also have a dissecting pad. Just went missing. Okay, so let's walk through this. You should have a manual. Gary's still out of it. Pop the manual open. We're gonna walk through real quick, get this stuff set up, start dissecting, get our hands filthy, and then at the end, if we run out of time, you're welcome to keep dissecting, do whatever you want. Do whatever you feel like doing. If you're curious about something we didn't talk about, do it anyway. Just wait till I'm gone. And then you'll throw everything away. Everything is disposable. It can be all wrapped in a bag, and I'll show you how to do that. But I want you to really actually just explore, be curious. If you have questions and you can't ask me directly while we're on here, then Google it is my piece of advice. In the meantime, go down here and hit chat. So if you do have a question while I'm here, type it over in the chat or have somebody that's near you, hopefully mom, dad, grandma, aunt, uncle, whoever, type it in the chat so you don't make your computer all disgusting. But I'll keep peeking up there to see if anybody's added anything. All right, you'll need the manual. Virtual Shark Lab Manual. So excited. We just finished making our second dissection set, which is organs from a sheep. It has heart, lung, bone, kidney, what else is in there? Eyeball, brain. It's pretty sweet. So we just made another book. All right, page 1. Thank you, Nicole, for putting the booklet together. She did an awesome job arranging this. I just wrote a lot of words and she made it pretty. So think like a scientist. This is actually, if you do any STEMs with me, this is the first thing I really promote is opening your mind and being creative. Think like a scientist. You were probably the best scientist when you were 2 weeks old, 2 months old, 2 years old, when you were a baby. So science is all about just being open-minded and looking around at things and questioning things and exploring things and testing things and learning what's wrong so you can do the right thing and learning what's right and making it better. So thinking like an experiment or like a scientist and creating experiments is exactly what we're doing today. You were born a scientist. When you were first born and just learning to move your arms and legs properly, if somebody showed you a yellow ball, you grab the ball and you pull it up to your mouth and you put it on your mouth and you learn the shape and you learn the texture, not just through your fingers, but actually through your lips. Because if you look at, and I love being in my lab again, if you look at a brain, kind of like this, human brain with all the parts labeled, our brain actually has an area here called the sensory cortex. It's on both sides. The side's labeled. And you can see everywhere in your body has little receptors that send signals to this part of the brain. And this is where your body senses touch everywhere. If you look at the proportions of them, you've got teeth, tongue, lips, face, nose, eye. This whole section is committed to your face. When you look at fingers, hand, arm, thumb, this whole section is committed to your arm, especially your hand, right? The rest of your body is the rest of this little bit. So your legs and your feet and your back and belly and all that, a small portion. You have the best touch sensation of your entire body in two places, your fingers and your mouth. And these little scientists take this yellow ball and stick it into their mouth to feel it, not to taste it necessarily, but to see what it feels like. So you're curious, you're exploring. And then your parents, every parent out there does this. They give you a lemon, right? Because they're smart Alex. We all love watching a baby suck on a lemon because of their first expression. So the baby takes the yellow lemon and puts it to their mouth and they grimace and they are freaked out by it a little bit. Maybe curious, want to try it again later. But they're learning, they're exploring. Now, every time that they pick up anything that's yellow and round, they're not going to shove it straight in their mouth. They're going to hesitate. They were curious. They explored. They tested something, learned something new, and they tweak how they do it. This is all about that. And you may be thinking, well, so I'm cutting a shark apart right now, but what will I do later? How will I change this or modify it? When you're eating dinner, be curious. I don't know if every kid does this, but this is the way I was. When I ate dinner, I actually dissected my stuff. I didn't even know I was interested in science or biology until I was, like I said, about 30 years old. But an egg, I loved cutting the membrane around the yolk and separating it from the white just because of that curiosity I had, trying to figure out how it separated. When I would eat chicken, I'd peel each of the muscle groups off at a time, not realizing they were muscle groups. To me, it was just meat. It was chicken. But be curious. And I blame your parents if you're not a super curious person. I'm hoping you are since you're here. But because when you turn 2, you're exploring your world. But when you turn 2, you've got all these new words. And the worst word that a parent wants to hear is why. Because when you learn that, you ask it over and over and over and over and over again until you just drive them crazy. So after a while, they explain to you, but then they start saying, oh, because I said so. And unfortunately, if you hear because I said so too many times, you start believing you do things just because you're supposed to, because someone tells you to, but not why. I'm not saying don't do what you're told. I'm saying be curious and ask why. When you get a job, when you got, and it doesn't matter if you're flipping burgers at the local fast food joint or whatever, if you do something a certain way, do the way you're supposed to do it, but ask why. Why am I doing it this way? If you ask questions like that, one of a couple of things will happen. One, you might just irritate your boss, but in a good way, hopefully. Another is that you might find a better way to do things. I mean, McDonald's came about because Ray Kroc thought we should automate the way that we do things so that every burger tastes the same and every burger's assembly is fast. And now look at McDonald's. It's one of the biggest, richest fast food franchises in the world. But it's because this guy who wasn't exactly a hamburger maker was curious about making the process better. That's all science. It's a scientific method. So when you were 2 and your parents were saying, because I said so, hopefully you get out of that and you start asking, well, I'll do it, but why do we do it this way? Why can't we change it, or why can't we try something new? So during this, I'm always open to questions. If you have something you want to dissect or you have a question about something, type it in the chat box, whichever way you put your chat box. But hopefully you're observing, you're seeing things during the dissection, or you've seen a shark before and you're curious about different things about the shark, and that's why you're doing this. So notice something that makes you wonder. The second thing is create a question. Ask why. So you see something and then you ask yourself, why does it work like that? When I was a kid and I had broken toys, I took them apart. My parents never knew where screwdrivers were because I always hoarded them in my bedroom, taking apart toys. And then I'd figure out what went wrong and I would try to fix it to make it right again or better. So question it. Make a hypothesis. Speculate or make a theory of why you think it is what it is. So when I took something apart, is it because of a loose wire? So I'd find the loose wire. And if I said to myself, I think it's because the wire of the battery is bad, I would take it apart. I'd go to the battery wire and look. If it wasn't, I'd have to redesign my experiment and start over. So hypothesize, create questions. You can do this with anatomy dissection. Observe the shark, question. So you see a shark, it's living, right? So it has to breathe. How does it get oxygen if it's in the water? I mean, we breathe oxygen from our air around us, but in the water, how does it get it? make a theory. Does it breathe with lungs? Maybe you think it breathes with another type of organ. So there's your hypothesis. Do the experiment, dissect down. Did you find lungs? If you didn't, then it has to be breathing with another organ. Find that organ, collect, analyze, and report your data, and then tweak it. So maybe you figured out that it doesn't breathe with lungs, it has to breathe with something else, which we'll talk about later. Next time you are in science class, whatever, and they dissect a frog, well, now you have two breathing organs. So it could be a lung or it could be this other organ. Ask yourself, modify, repeat, and see if you can find it. So what's interesting is the frog actually can breathe with its skin. Just a spoiler alert. Next. So find your questions, test it. If you're in the eyeball and you want to know more about it and we don't have time to do it, set the eyeball to the side and dissect it afterwards the rest of the way. If you want to know about the muscles around the eye and see how they work, play with them. We're not going to talk much about it, but do what you want. We're not going to dissect out muscles very much in the shark body, but if you're curious, I'll show you while we're doing this how you can dissect to the muscles and find out what's moving what. Right? Have the right tools. And this is actually what we're talking about now. Having the right tools isn't about a pair of goggles or a pen. It's more what you can do with the pen because of what's between your ears. So the right tool or the best tool for questioning or experimenting or becoming a researcher or a doctor or any kind of scientist is having the right tool between your ears. Be curious, be open-minded. When someone says something, be a skeptic. I'm the worst skeptic. It drives my partner nuts sometimes, but I'll ask her why all the time, or why do we do this that way, or why should we do this, and why can't we do something in a different way that might be better, maybe worse. So we change our mind. Just keep exploring, not just exploring by walking around space, but questioning everything, wondering how things work. I still to this day rip things apart just to figure out how they work. I get all kinds of old expired tools from the hospital and I rip them apart and see what we can do with them. It's just a fun thing to do. The right tool or the best tool is actually the one between your ears. Get prepared. This is where the kit came in that you got from us. So here are the things you're going to have to use to keep your brain safe. We don't want anything getting into you that shouldn't be. The smell of the fish, it's a really fishy smell. It has a preservative called formalin and some other preservatives in it. It used to be called formaldehyde. It was it's not formalin, it was formaldehyde. But formalin's a safer version of it. And people were worried about formaldehyde because if too much of it can be bad. But what people don't realize is that, and here's your scientist, Google what in your house has formaldehyde in it, and you're going to be really surprised. Do you have carpet in your house? You ever walked outside and like the grass and in the woods or whatever, or the mud that's full of bacteria and fungus, and you walk in, you put it on your carpet? Why is it that fungus grows outside but it doesn't grow in your carpet? It's formaldehyde. Your carpet's full of formaldehyde. You ever sat on the couch and spilled something on it and it didn't like mold on the couch? It's because the coverings are full of formaldehyde. Paint has formaldehyde in it, so when you paint your walls, they don't mold ideally. But look around at what's in your house and then Google online what has formaldehyde in it. You might be surprised. It's all over the place. But it's a preservative. It's to preserve things in your house, preserve fish, sharks, animals. I have a brain that's behind me that's soaking in a jar of formaldehyde. So we want to protect you and keep you safe. The first thing we're going to do is make sure you have the proper personal protective equipment, which is PPE. You need gloves. You should have received a pair of gloves. I can't remember if they're smalls or mediums. I know they're not larges. I actually don't like using large in my lab, even though I'm a large size, because I like everything to fit tight. So I always wear something that's smaller, and I make sure that the fingers are pulled tight. Of all the hand, the fingers have to be tight. It's because when you're feeling something, you want to make sure you can feel the folds or the creases. When I have you feel the skin of the shark, I want to make sure you can feel the texture of the shark. So when you put the gloves on, put them on tight. If you rip a glove, grab a Ziploc bag, or you can even grab this jump bag or a grocery sack or something. Grocery sacks are great because they're really thin. So you can feel really well through a grocery sack. Ziploc bags are great because they're clear and you can see where your fingers are. And I'm not saying that because I don't want the formaldehyde on or formalin on your fingers. It's because it smells. It's stinky. That fishy smell, if you get it on your bare skin, it's going to stay like that for days. So if you rip your glove and you keep using this, when you go to pick your nose, you're going to smell that fish. And it could be good, then you don't pick your nose anymore in public. But at the same time, you don't really want to Yeah, you don't want that smell because other people can smell it even when you can't. Eye protection. You have goggles, disposable ones that came with it. They're there. If you have glasses on, like I do, my glasses are actually slightly bigger than the goggles. So when I use my glasses, this rests just above my cheek. And the whole point of the goggles is that anything that splashes up, you don't want it to go underneath. So you keep the goggles on tight or your glasses on tight. You wear them so that if anything splashes in general, it protects your eye. If you get a little bit something that splashes in your face, just go to the sink. So it says right here, nearby sink, and just tilt your head sideways, just like this, underneath the sink, and let it run through and over your eye so that you get it all off. I don't know if you saw that, but just tilt your head sideways and let it run. They say 5 to 10 minutes. Run till you're comfortable. Let it run till you're comfortable. I've never had formalin in my eye. I don't know if it's stinging or not. It's kind of oily, so I would imagine it just feels gross. But you have to let it run by. So eye protection, apron, lab coat. I have my lab coat on. You were given an apron. When you open up the apron, it has a set of straps to go around your neck. It has a set to go around your waist. So just make sure you put it on. It's to keep this stuff off your clothes. Remember, formalin, formaldehyde's in the fabrics around you. If it gets on it, it likes to stay on it, so you might stain your clothes and it might permanently smell like fishiness. So just keep that off of you. Nearby sink, I already said that. If you're in the garage, make sure there's a bathroom that you know you have a quick path to. Make sure there's an adult near you, like in the next room or somewhere that they can hear you and you can see them, so that you know if they leave and you know how to play it extra safe. But if something happens, yell for them, have them escort you to the bathroom to rinse your eyes. If you rip a glove, yell for them, see if they can bring you a sack. You know? Yeah, if you poke yourself, if you need a Band-Aid or whatever. Push poking yourself, sharps and specimen safe disposal. We have a big bag that we're going to do everything on. When you're done, you're going to roll it all up in the bag. Super simple. I hate taking the time to clean, so I just keep myself in a tidy situation all the time so that I can work in a space. And when I'm done, I just roll up the space and pitch it. I don't have to worry about being super clean. I like to be clean, but I don't like cleaning. All right, so sharps, specimen. The sharps themselves, when you get it out, you'll have 3 sharps. So you should have a, uh-oh, my board's gone. I put my board in the bag and forgot it. Think. So you should have a set like this. You've got the cushion. You have 6 pins. 1, 2, 3, 4, 5, 6. Always know if you have 7 pins or 5, it doesn't matter. You just need to know where they're at all the time because they are sharp. And if they have formalin on them and they poke into your skin, it'll irritate your skin, make it turn a little puffy and red. So you don't want to grab it. And you don't want to squeeze on it and stab it right through your hand. So always keep your sharps protected. You have a pair of scissors. You can see how I store my scissors, either in the top or I poke them down in. If you have the rounded scissors, which I prefer, I don't have any near me, you can still do the same thing, or you can just slide them underneath the mat just so that it's protected. And then you have a probe. It's like this. Yours is shorter, but it's thicker and it's better than mine. Sharp tip here has a flat edge on the other side, but you can either stick it into the like that or to the top, however. This one I have breaks way too easy, so I'm jealous of the ones you have. Those are your sharps. Always know where they are. It drives me crazy when med students or residents, which are new doctors or the surgeons, come in here and they're using needles or they're using suture needles or injectable needles or a scalpel, and they just leave it on the table because someone else could come along and put something on top of it where they couldn't see it, and then they go to grab a pen and they cut themselves on a scalpel. Always know where your sharps are. Always know how many you have and keep track of them. That's the science protective, fatherly, whatever geek inside of me. But I'm always worried about people getting cut, especially in labs. Right? You don't want anything in a lab inside of you. You never know where it's been, really. And then I also said adult within sight and sound. So not just where you can yell for them, but make sure they're there. Because if you yell and they're not there, that's not good. Never good. All right. So you have your apron on. You have your gloves on. You have your goggles on. Those are your 3 pieces of personal protective equipment. Make sure they're on. You have the dissection manual, which we're looking through. You have a dogfish shark. It's not a baby. It's actually over 2 feet long. The babies are little guys. We originally started with baby sharks because it was funny just to say baby shark. But we found out they're too small to dissect. So now you have 2 foot long plus sharks, which are awesome. You can really get in there and see what they ate. Hopefully they had a big meal before we cut into them. They're just huge. They're awesome. And they keep getting bigger every time we do this, which is great. We don't have dissection trays anymore. Instead, you have the black plastic bag. But dissection tools, you have a set of tweezers that look like that. You have a ruler that looks like this. Mine's all bent up, but it still works, measures. And all these are disposable too. I laminate my ruler so that I can keep using it over and over again. Ruler, scissors, which we just saw. There are all kinds of different scissors. I prefer the rounded tip. These are actually not the rounded tip. I'm using the leftovers from what we've done before, so unfortunately. Probe, which is the wood stick, and then pins, right? You have a table cover, which is also your disposable bag, and that's what we're going to use now. Your hands are clean. Mine are a little bit oily, so I'm going to change my gloves as I do this. But you, with your clean hands, are going to remove everything off your table. Sliding all my stuff on the bag. Because we're going to put this black bag down as a tablecloth so that everything we do doesn't get on mom and dad's table, grandma, grandpa's table, aunt, uncle's table, whoever's table it is. And hopefully you're doing this outside, but if you're in the kitchen, you definitely don't want to spill this on the floor in there. So I'm going to flip back to me for just a second. I think now I've got a knack for flipping. Yeah, there we go. Oops. Got my coffee. Don't drink in the lab. Okay. Surgical lights, right. Don't open this completely up. You're going to open it just a little bit until you find the end that has the seam. So if this were a trash bag you're putting in your trash, you've got the seam right there. I don't know how well you can see it, but there's the end of the bag and there's a little, almost like, looks stitched going along. That's the end that doesn't open. That's the end you want to grab. Don't open the bag like you're putting it in a garbage can. You're going to open it flat. This. Now you have a huge tablecloth. Slide it down on. You can see my table, but I have a lip on my table, which makes it nice so I don't spill anything off the edges. Nice and flat. Perfect. Okay. So you have this table. I'm going to tilt this light away just a little bit. And now you can set your stuff back up. I have my handy dandy placemat, which you don't have, you don't need. This is just for us to use to say thank you for the people that helped us send this to you, like PNC. Actually gave us a bunch of financial support so that we can get the kits out really inexpensive so that you all at home can learn from the comfort of your own home. And of course, OSF, who owns Jump Simulation, which sends me a paycheck. So I'm very grateful here. University of Illinois also covers me and supports all of this because Jump is a collaboration between these two, the educators and the people that actually put them to use. Next thing I'm going to do is I'm going to put my pad down. Actually, I'm going to put gloves back on. Like them off. Second. Okay. Pad's back, right here. And then it still has my pins across the top. I'm gonna slide this down. Sorry, jump. Right. My pins across the top, my probe, my scissors, my ruler. I'll sit over here to the edge. My pen for writing. You're gonna throw this away when you're done too. So, whoop. I like to take notes in my manual, and then at the end, instead of keeping the manual, I clean my hands and then I slowly flip and take pictures with my phone of the pages I put notes on, or I jot them on another piece of paper. If you want another manual, I can send a link to you that you can print it at home too. So if you want to keep dissecting. And by the way, the repeat part of dissection, you can buy a fish in a store. You can go to like a Kroger or Walmart and buy a whole fish like that you would eat and dissect it. You don't want to buy a fish? Grab some string and a hook and a worm, right? Go catch it. And then as you're cleaning it to prepare it for eating, you dissect it. That's actually the funny story about me, is that I don't like hunting. My whole family are hunters. And the first time I killed something, I said, I'm never doing it again. So to make me a man, back in the old days, to make me a man, I had to clean all of the animals that they killed. So deer, squirrel, geese, fish, whatever. I had to do that. And I said, ugh, gross, never again. And now look what I do for a living. Crazy. Okay, so we have all of our stuff that's in here. I think I brought everything back to the table. Oh, there are tweezers, pen, ruler, yep. Got it all. You should have goggles on your face, gloves on your hands, apron on the front of you, and that accounts for everything. Perfect. Cool. Let's go. Autopsy time. So, jump steam at home lesson and baby shark autopsy. First, not a baby. Whoop. And it's also not an autopsy. So what's kind of cool is that when we start working at Jump again and letting STEM students back in, we do a pig autopsy where you spend a day with a group and you go through a full autopsy of everything, just like we're doing with the shark, but with a pig, and you try and find the cause of death, et cetera, et cetera. So I wanted to point out that that's not a real autopsy. We do it as a forensic or criminal autopsy practice, but autopsy, auto means self, opsy is to visually look and take apart or visually inspect something. So when you do an autopsy, you're actually cutting yourself apart. So people that do autopsies don't cut themselves apart, but what they do is they cut other humans apart. So it would be a human cutting another human apart. That's autopsy. This is not an autopsy. This is a necropsy. So we're down, somewhere down here. There it is, necropsy. So since you, a human, are going to be performing necropsy on another animal, you're an animal, don't forget that. It always drives me crazy when people say, well, animals, not like humans, but animals. No, you are an animal. So when we cut apart another animal, like a quadruped, which would be a, like a dog or cat, something that walks on 4 legs, it's considered a necropsy. So if someone's performing a necropsy, who would do it? I guess legally, who would be the person that would do it? Well, who would do an autopsy legally? It would be somebody with some kind of a medical or research degree, right? So it's a person, a doctor, like an MD or a DO or PhD or something, that's cutting apart another person to find out the cause of death. What kind of person would cut apart another animal? Who works on animals? A veterinarian, right? So veterinarians typically do necropsies. Why would it be important? And I had to think about it for a second. I was like, phew. Okay, well, when your pet dies, usually it's of old age and natural causes, and they don't need to do a necropsy. But why would they do necropsies? Why would they take them apart? And then I had raccoons in my basement, and I started thinking about the raccoons and thinking deeper, and I thought, what if something killed raccoons and nobody knew why? A veterinarian would actually have to do the necropsy, set it under a microscope, send off lab tests, analyze all the parts, see if everything's working. So if a park ranger were out in the forest and they were driving along, say, saw a dead raccoon on the side of the road, they would pick it up and put it in their truck, take it back and have it disposed of. But they keep driving and they find another raccoon and another raccoon. And before they know it, they have 5 raccoons. There's something weird about that. Unless they were all hit by a car, which is obvious cause of death. was killing the raccoons. So they would take them to a veterinarian. The veterinarian would look inside, see if there's any visible cause of death on gross anatomy, the overall, what you see, dissect them down, take slides of different organs, send them off to a lab to be analyzed, look at them under a microscope, do tests on their blood, and they would be looking for something that might be causing death of raccoons. Like maybe there's a virus. We're in the age of Corona and COVID-19. Maybe there's a virus that's killing raccoons. And if it spreads across the country, you have an epidemic. If it spreads across the world, you have a pandemic. And it's something that would have to be taken care of because strangely, raccoons actually have a place, good things that they do, like eat critters that we don't want around, right? So we'd have to find out, and that would be a necropsy that's performed. So you are technically doing a necropsy on the shark, right? A little more about the shark. It's a dogfish shark. It's actually a fish, right? All sharks are fish. They're a special kind of fish. So sharks are a primitive fish. They're a primitive creature in general, not like when we think of primitive human and caveman, whatever, where they're really dumb. Sharks are really smart. Most sharks are really smart. But primitive means that they're really old. And so when you think about a shark, living sharks today have ancestors that were alive 125 million years ago. I was just talking to an engineer at Jump, and he said, "Did you know that sharks are older than trees?" And I said, "What?" And I really have to look it up. So I can't confirm or deny until I look it up. But when he said that, and I started thinking, actually, yeah, microbes were around before plants were. So it's possible that sharks are older than trees. Crazy. So very primitive. Spiny dogfish. Spiny, when you look at it, there's going to be a little piece of tissue missing here and a little piece of tissue missing here. Because just like a catfish, if you ever caught a catfish, there's a spine that goes off the dorsal or the back of the dogfish shark that's filled with a toxin. So the fishermen remove that before they even send it to the place that packs these for us. So you won't see it, but you will see the little tube that's like a syringe or a needle for injection. And think about why you would want, if you were a dogfish shark and their size, and why you would want that spike there instead of somewhere where you could use it as an attack structure. But we'll talk about that too. These are also called cartilaginous fish. Cartilage, because their skeleton is made of cartilage. There's no bone at all in a shark. No bones. Teeth are not bones, but they do have teeth. They're hard, super hard, and other structures that are like teeth. But their skeleton is actually cartilage. So when you look at the words, there are about 1,000 species of cartilage fish. Ichthyes is referring to fishes, types of fish or a fish. Chondra is referring to cartilage. So another big thing, if you're thinking about going into medicine or any kind of research around medicine, is pieces of words. The word chondra, C-O-N-D, handwriting gets worse every time. Chondra means cartilage, cyte means cell. So if you're doing research and you're studying a chondrocyte, you're studying a cartilage-making cell. Your nose, your ears have chondrocytes in them that make cartilage. So chondroichthyes are cartilage fish. About 400 of those are actually sharks. There are other things that are not sharks, like a lamprey. It has a cartilage skeleton too, but it's not a shark. It actually doesn't have a jaw. Sharks are one of the oldest creatures with jaws in them too. I wonder if that's why they came up with the movie name. Probably not. They're usually ectothermic. Ectothermic means it gets its temperature from its surroundings, like a snake. So if you know anything about snakes in the wintertime and they go down in a hole and they coil up in a ball, they're still alive. They don't move because it's so cold. Their blood and circulation slow down, their metabolism slow down. Sharks are the same way. Most sharks, I need to say that, usually, and most sharks. So ectothermic means that sharks usually have a water temperature they like to swim in. Like they'll swim in the warm ocean water, and they don't go much outside of that temperature because they depend on that climate. Because if they move into the colder temperatures, just like a snake, their metabolism slows down. They don't swim very fast. It's hard for them to catch their prey, and then they'll probably die. So not because they freeze to death, but because they'll probably starve to death first. However, some are endothermic. Endo means within. They make their temperature thermic. Within. You are endothermic. Think about it. When you're cold, yeah, you might like to curl up in a ball because it helps you hold the temperature in, but what else do? You shiver, right? And the shivering creates friction in your muscles. It warms your blood. That blood flows through your body and warms the rest of you up. That's what endothermic animals do. Some sharks do this, like the bull shark. If you did the pre-lab stuff that we sent out, which you didn't have to, this isn't school, right? It's fun learning. But the bull shark is actually what the movie Jaws was based after, not the great white shark. But the bull shark is endothermic, which means it can go into colder waters. It can also go into fresh water. We hear about sharks in salt water, but these bull sharks, the story Jaws was based off of them going like New Jersey and New York and stuff, but which is close to an ocean. But bull sharks have actually been seen in the Illinois River. So they'll, you know, I'm not the best with drawing the map of the United States, especially with my Florida, my Texas, and California. But in the Gulf of Mexico, they'll swim all the way up the Mississippi River and actually come into the Illinois River, where you don't normally see a shark. And they have their babies there. They're sharks, right? So they're aggressive. Most of the fish we have in the Illinois River aren't that nasty. So these baby sharks have a feeding frenzy on the local fish. They get all full, swim back down, and then they hang out with their buddies and play with the other sharks in the Gulf of Mexico in the ocean. So sharks that are endothermic actually have a way of warming their blood. If you ever have a slice of tuna and you see that really dark red area, it's because those muscles, the red area are muscles, are full of blood. And when the tuna's cold, it actually uses that muscle to warm the blood. So they're endothermic. Tuna can go all over the place because they're also endothermic. All right, and then here's the big, why are we doing what we're doing? But even though sharks spend their life in the water, they have to breathe oxygen, right? So why? What makes them different than us? We're doing comparative anatomy. We're comparing our systems, which hopefully you've learned a little bit about it in school since you're in high school, to the sharks' systems. They have all the same systems. They just work a little bit differently. So we'll compare the similarities like breathing and how they breathe. We'll talk about their body structure, like paired appendages, like we have arms and legs, 2 of each. They have fins that work and come in similarly. Digestive process, how they eat their food, process it, and how it's like us and how it's different. And if you want to see how closely related we are, Google taxonomy of shark and human, and there are a lot of web pages that show you how far away are we based on all the species out on the planet. Kind of fun. I know it's learning, but I'm a geek. I mean, let's just face it, I'm a geek. I don't go to rehab for geekness or anything like that. I embrace it and I love it. But I'm an actually person. And if you've had a STEM with me before, you know that one of my favorite things about learning is that finding that 1 or 2 things that are so cool that when someone talks about that topic, I can say, actually, and then I can give my feedback. Because I love those cool little things. Man, I walked into the lab across the hall and someone goes, hey, give me a cool shark fact. I'm like, what? But I love those fun things. External examination, we're going to actually open up our shark and look at it externally. We're going to describe some of the directions and terms you need to know, and then we'll start doing some measuring and cutting. So put that down, grab your shark. I have a 2-pack, and I'm actually going to switch cameras so that I can show you how to unpack the shark. Hopefully you haven't unpacked it yet. So your shark's packed in a bag or 2 bags. When you make sure there are no leaks in the bags. That one's gone. Excuse me. Something dusty just flew in my face. When you're unpacking this, make sure the head is up, tail's down, head's up. You see the juice usually gathers around the tail, like that. When we cut this open, you're going to cut the head side. You're going to dump the juice out into a trash can or container or whatever. And when you're done with the bag, you're going to leave the bag upright because there's still going to be juice in there. But don't do anything yet. When you cut it, you can see the seam along the top. Just cut just below the seam just so it opens up. Once you puncture this, the vacuum will break. You're going to cut along, open it, dump out the juice. If you're at a sink and you feel like rinsing a little bit, you can. But when you bring this back to your table, make sure it's in the bag. Don't just walk across a room or anywhere, even outside with the stuff dripping, because you're going to kick it. You're going to get down on the floor. It's going to be a mess. So you're going to cut across here. You can drain the juice out. leave the shark in the bag, bring the bag back. When you pull the shark out, you'll pull it out, let it drip in the bag for a second or two, put it on the table, put your bag upright in a trash can so it doesn't spill. So what's weird is that my sink is actually broken, so I have to go back to that room and use a sink. So I'm going to do exactly the same thing that I just told you to do, and I'll meet you back here in like a minute. Grab your scissors, your bag. And I'm being patient. If you're still getting it and you can hear me, I'm just waiting to watch for people. So I would still use the black garbage bag for the question, because we're just going to roll everything into the garbage bag when we're done. Like turn it inside out, right over the pad, the shark, everything, and you'll hold it and drop it in the trash and you're done. With that disposable tablecloth, you'll want to dispose of it if this stuff hits it. All right, and then the cat's tongue, I'm assuming you mean the skin. Feels like a cat's tongue. And there's a reason why. Okay, so again, grabbing my shirt. Bag's upright, shark's over the table, laying it down. Bag's still upright, and I'm just gonna put it in the trash so it's standing and it doesn't spill anywhere. All right, time to flip back. Boop. I watched Toy Story too much. I'm imagining Sharky. Howdy, 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 I'm Woody. All right. Okay, anatomy. The terms are really important. And you'll see that a lot of these terms we actually use in day-to-day life and probably didn't realize it. But when we're doing comparative anatomy, we're trying to compare the human to anything else. We just put together another of these dissections with sheep organs, with the brain, eyeball, heart, lungs, all of that, and we compare there. Even when you're comparing like starfish, we're building one that you'll dissect a starfish and an octopus and a squid and a fish, blah, blah, blah. One locally with a turtle, a frog. I can't remember what else was in that kit, but we're trying to put together a bunch of these dissection kits. all based on comparative anatomy, so that when you look at a human, you can see what's different about us compared to these other organisms, because we have a lot of similarities. When we use the terms, most terms are interchangeable. If you're going to become a doctor, you have to learn medical terms, because when you write out a chart, it's a legal document, and the terminology has to be specific, and it has to be in medical terminology. It has to be so that any other doctor can pick that up and know exactly what you're talking about. So whether it's distance down to the millimeter, or if it's talking about bruise, how big the bruise is, what color it is, it all has to be very specific. Anatomy, when we say something's above, we don't say it's above it, because that could be closer to the skin. So if it's if it's something on their heart and you say above it, are you talking about above towards the head, or above, like if they're laying on a table and it's closer to their chest? You never know. So these are the terms. In human anatomy, we say medial is close to the middle. We don't say it's near the middle of the body. We say it's medial to something else. If we are going to the outside edge, it's lateral. So if I'm looking at the shark, I'm looking at the fins, I would refer to this fin as lateral to this one. Even though they're not exactly on the same plane, if I'm just describing it, I would say that this is lateral to that. Or I would say this is medial to that. So I would say the dorsal fin is medial to the pectoral fin, or vice versa. Flip it around. If I'm saying something's above, and I really mean up and down, I would say, well, on a fish it's slightly different, but on a human, like this. It's superior, it means above. Like your boss is your superior. You're their inferior. So inferior is below. Depending on the perspective of the fish, this can change. So this is for human, but this is for most animals, like quadrupeds, like a dog, a cat, a cow, because their head faces forward like this, not like us. Our head doesn't go in line with the rest of our body. Our head actually tilts like that. Where the other ones, if you take their spine and go straight, their head's straight with the spine. Ours, our spine goes up, and then boom, our face goes perpendicular to it. It's different. So anterior means to the front. Anterior also means to the front here. So my face is anterior to my brain. The fish's face is anterior to their brain. Posterior means the back. So my tushy's on my posterior. Posterior or caudal means close to the tail on a quadruped. Anterior cranial means close to the head on other animals. Dorsal means the back of a fish or a dog, right? Or well, any other animals besides human. We typically don't use dorsal except in the brain. And then ventral is the front side, where we would use anterior, talking about our front in general. They use ventral in general. So, and I know that gets tricky because of the word anterior being there. But human, here are the exceptions to how it's a little bit different. And it's nice because we name the structures in the body after the anatomy. So if you have two of something, we will refer to it as the superior and the inferior glomella, which are little structures in the brain, okay? So the superior one you'd find above the inferior ones. They describe where they are. Let's see. Proximal distal. Proximal means close to the middle of the body, not like medial. Medial means you're just moving towards the midline. It could be at different layers in the body, but it's moving towards the midline. Proximal means close to the body itself. Proximal and distal usually refer to the arms and legs or the fins. Proximal means if you hold your arm out, your wrist is proximal to, which means compared to, your fingers. Your fingers are distal or further away from your body than your wrist. So we would say the fingers are distal to the wrist. Right? We say the fingers are distal to the elbow too. It's just comparing two things. Superficial means close to the surface. Deep means deep inside. So if I were talking about bones in the heart, the heart is deep to the rib cage. Boom. The rib cage is superficial to the heart. Just comparing. And then these planes, a sagittal plane means you're cutting it right down the middle and separating left from right, which we'll do when we get into the belly. Where that folds at, we'll cut along that, and that's a sagittal cut. A transverse means across. Like you can see where these arrows go, those are in a transverse plane. So when we get into the chest, we'll actually make a transverse cut from this side across. Frontal means you're cutting the front off of something. So if I had something that would peel my face off, that would be a frontal cut. What a weird, morbid thing for me to pop into my mind. Crazy. But there it was. So it's actually, by the way, I'm popping over to the chat. Formalin is the chemical, and formalin is not as toxic as formaldehyde, but it's a lot like an onion. How an onion makes your eyes tingle, same thing. Some of the chemicals get in and just irritate the mucous membranes that make your eyes a little runny sometime or burn your nose. It's just saying, hey, don't drink this. All right, so those are the planes, those are the anatomical directions. Let's put them in action. So if I use some of these words, dorsal. If I have a dorsal fin, which one am I looking for? Right, dorsal side, it's the most dorsal. There's one. You have just one? You have two. Come back here too. And remember how I told you the dorsal fin was missing something? See how that's been cut? And that's been cut? You can usually, you might have to look down a little bit, but in mine, you can see where that needle came out, that spine came out, and there's actually a little hole inside the spine with the toxin in it. It's not toxic to humans, it's toxic to other fish, but it would, if they left it on there and it poked in your finger, it'd make it red, irritated, itchy, and burn. Ugh, gross. Okay, so dorsal fin helps you identify where it is. How about pectoral fin? Think about humans. Where's the pectoral region on a human? Oh. When I think of pectorals, I always think of bodybuilders that are going to the gym and they're like, hey man, look at me, I'm buff. Yeah, yeah. Right? So the pectoral region's right through here. So in us, we have two muscles on each side. We have a pec major, pectoralis major, that goes across on this side and this side, and then a minor one underneath. Major just means bigger, minor means lesser. Okay. So, sorry, pectoral fins are the ones that attach to the pectoral region. Here are your pectoral fins. These are actually unique because these fins are not like normal fish fins. These are cartilaginous fish. The shark group specifically doesn't wobble their fin like a bony fish. A bony fish is all the other fish that you're probably familiar with, like a bluegill or a catfish or carp or trout or whatever, swordfish, any of the other big fish. But with bony fish, they can move their fin around. If you look at a goldfish in an aquarium, when it's sitting still, it's waving its fin like that. Sharks can't do that. Sharks don't have a lot of muscle in here. Their muscle is primarily to tilt up and down like this, because their fins act more like wings on an airplane. And wings on an airplane don't flop up and down. They just bend the back part so that when they're moving forward, they can steer, right? Push up, shoom, pull down. That's how these are. So they're more like a wing than a flipper. It's kind of interesting. When you look at the fins are primarily for steering, balance. So to keep them from spinning, they're like a torpedo. And if you didn't have the fins, they'd just keep spinning around in circles, right? And minimally for propelling or moving forward. Most of the propulsion is actually because of the muscles, and we'll talk about that. This is more like a rudder on a boat that helps steer the boat. All right, so the pectoral fins, we talked about the dorsal fins. Thinking back at parts of the body, pelvis. Your pelvis is your hip region, right? So if these are the arms, and this is the pectoral region, go down, down, there they are. And you can feel. This is like where the leg would connect to the hips. You can feel right across here. There's a strap, like the front of your hips. You have your pubic bones, and the pubic symphysis is a little piece of cartilage on a human right here. Same way. Here's where the legs would be. So pelvic fins are the ones going off the hips. It's a good time to say whether you have a male or female, so you can refer to your shark appropriately. On the pelvic fins, if there's a second, see that split right there? And it looks like a second fin coming off, it's a boy. See it? Same way over here. There's a split. Girls won't have that. Girls will just have this fin and it comes straight, no splits. Okay. Next, caudal fin. So that's the anatomy again, the directions. Where's caudal? Is it referring to towards the head or towards the tail? Towards the tail. So the caudal fins are at the very end of the tail, paired. So some say that they're one single one, but others say it's paired because they're different shapes. Depending on the shark, I guess. Some have a real long whip on the tip so they can snap things. Others just use it like rudders. Some have big floppy ones. Those are the ones that just look pretty and not really practical. But this is more like a rudder because this is a fast shark. So we have pectoral fins up here at the front, 2 of them. Dorsal fins, 2 of them at the back. Pelvic fins, 2 of them down here at the hip region. And then 1/2 of the caudal fin. So either 7 or 8, depending on what book you go by. Right, lateral line, kind of a cool feature of a shark. And you can kind of see it. See that faint line that goes all the way down? Why would they call it lateral? Because lateral means to the side. The faint line that goes all the way down the side, comes along, goes along the tail, and all the way back, and it follows, just keeps going, keeps going, keeps going. And you can see it coming all the way down to the tip. The lateral line is actually a sensory organ. So it has a special sensation you don't have, and we'll talk about that later. And that lateral line are all the little structures in it. Gills, here. Bony fish, like a bluegill or a goldfish, actually have a bony structure that covers it. It's a gill cover. And when they're trying to breathe, you'll see them moving that gill cover because what they're doing is they're pushing water over their gills all the time so that they can breathe. Sharks don't have that. Sharks have to bring water either into the spiracle or through their mouth and out through the gill. So if you're curious, like I'm always curious, you can take your probe, take the dull side of the probe. If you want, stick it in. Put my finger in. Ow, bit me. I'm kidding, didn't bite me. May have to try this later. This fish is kind of plump. So pull out a spiracle. How about go in here? Go into the mouth, and you're aiming for the gills. Wow. Mine's really rigor mortis-y. There we go. Put this in and kind of feel for the side. No, mine's too rigor mortis-y again. Guess we're gonna have to cut it open. Dang, huh? Well, I can see it trying to poke out here, but yeah, it's a little too firm. Let's see if I can go in the other way. So I'm going against the grain, kind of wiggling in. There we go. So you can see that pathway goes straight mouth. So water flows in, goes to the back of the mouth, goes out the gills. So sharks are constantly swimming so they can get that water either flowing into the spiracle and down or into the mouth or down, or some sharks have the spiracle, which is on the checklist, for breathing. Great white sharks don't have this. So a great white shark has to swim all the time or they die. They always have to have water going in, going over the gills, grabbing oxygen, and then going out. Sharks with a spiracle can actually suck water in here, puff their cheeks up, squeeze their cheeks, and blow it out their gill. That would be like you putting food into your mouth, sucking it in, holding your chest tight, and then blowing out your nose. You ever done that with soda? Stingy. That's all I gotta say, it's stingy. You think formaldehyde stings your nose. Whew, try a Pepsi. All right, lateral line, gills, spiracle. That's that little round structure we just pointed at. Eye, I think you figured out where the eye is. We'll actually remove one of those later. Nostril or nair, it's not a nose. Flip it over, there's a nair. If you look in there, you can kind of open it up a little bit and take a peek in. Some of the things that you're looking at on the camera, my camera is not the best, so it gets a little blurry, but these are blind openings, not because they're for vision, but because they don't go anywhere. It's just a hole. Whatever comes in here stays in here and then gets squirted back out. It's not like us where you put something in your nose, it goes to the back of your airway and down. These are blind-ended. They're only there for smell. The end. And they're called nairs. The nose up here, the tip, is called the rostrum. That's the technical name. It's not a nose, it's a rostrum. And sometimes with directions, we'll refer to it something being rostral, which means towards the nose. Right? And then, of course, the mouth. And if you want to open, Check out those chompers. Nice. Open up and say, ah. Check out those teeth. See how many rows of teeth we have here. We got 1, 2, 3. 3 rows on this guy. So when a shark loses a tooth, blink, it doesn't get it doesn't get cavities. There's that 1 row up here, a middle row, and a back row. It pops the tooth out, swallows the tooth, recycles it for the calcium, and then one of these back teeth will actually move up into that position. So the front row is actually just constantly being recycled from other rows. That's the mouth. Its jaw feels hard, no bone, it's all cartilage. We'll cut it later and show you. Awesome, let's measure this bad guy. So I refer to mine as the eye because mine's a male. Be courteous or be sensitive if it's a female. She this, she that. Okay, we're going to measure it. So here's our first problem. I've got a 12-inch ruler, almost 31 centimeters long, but I've got a fish that's considerably longer. So how am I going to measure this thing? Originally, we wanted the baby sharks, but they were so tiny and just wasn't worth it. We got the monsters. This is great. These sharks are probably 4 or 5 years old at least. Right. Here's how we're going to do this. I'm going to, and it says measure it in centimeters, so I need to make sure I get the right side. I'm going to start right here at the nose. Notice that the end isn't the beginning. There's a 0 tick mark. So bring it to the 0 at the nose. I laminated mine. Actually, Annie laminated it for me because she helps out with all the stuff so that I can rewash mine over and over again, which I'm finding out is a pain because it's hard for me to stick exactly on the mark with a laminated one. So I'm going to slide this down just so you can see what I'm doing. You saw me put it up to the 0. There you go, 0. I'm holding it down completely, following along, making sure it doesn't slip. And I'm going to take a pin and put the pin right at the 30 mark. When I poke it in, it's going to pop a little bit. Pop. Just put it into the pop. So we'll talk about the skin. The skin's really tough. You just have to break through it, and then you're into muscle. So there's the first pin right there. Now I'll just move my ruler down. Take that to the 0 mark. Grab another pin. We got a big fish. Oh, a little further. All right, at the 0 mark. Holding it in place, going around here, getting as straight as I can. And 30. Second pin. And go from that pin to the longest tip on the tail. Get down there. I'll slide it back and forth just a little bit to see where I can get the furthest. Wow, that looks like 12.8. We're going with 12.8. All right. It asked me how long is it. So I've got, wow, this book got drenched pretty fast. See the back of the fin, it's about 30. Yikes. From here to this is about another 30, and then 12.8. So I've got 72.8 centimeters. To find out how many inches, you can measure again, but I just use a calculator. I usually have somebody around with a calculator if they walked out the door. But anyway, we divide this by 2.54. So for every 1 inch, there's 2.54 centimeters in it. Echo. What is 72.8 divided by 2.54?
72.8 divided by 2.54 is
There, you heard it. 28.66 technically, so 28.7 inches. Echo bosses me around at work and at home, but she's also very helpful. So 28.7 inches. That's my overall length. If you have somebody that's helping you that can touch your computer, you can have them type your numbers up in the group chat. We're not going to calculate them now, but you can later to see how your fish compares, your shark compares. You just add up all of the, do it in centimeters, by the way, sorry. It's easier to get a nice round number without using percentages or ratios, or not ratios, what's the word I'm looking for? 3/4 of an inch kind of thing. So anyway, 72.8, boom. You'd add all of them up, take the number that you had. So if we have 24 kids in here, it'd come up to 1,000 whatever, divided by 24, and it gives you the average. You can see if you have the big fish or if you're less than average. All right, I'm taking pins out. 1 pin, 2 pin, 3, 4, 5, 6 of them all together. So 2 up here, don't know what I'm doing. 6. All right. Next, it asks for the wingspan. Remember how I told you the fins are like wings on a plane? You don't want to stick them straight out. You want to hold them so they're comfortable. Hold it, and take those 2 pins, boom, stick them back. Now it's pinned. So wingspan, you're going from tip of wing to tip of wing. You can do it with birds, you can do it with sharks, you can do it with airplanes, you can do it with us. We just don't have wings, but we still measure. If you hold your arms laterally as far as you can apart and you measure, that's your wingspan. I don't want to do inches. I like doing centimeters. If you haven't heard, inches is the British, it's called the British system. And the United States is one of the few places in the entire world that still uses it. Miles and inches and feet. In fact, Britain doesn't use the British system. They use metric, centimeters. All right, so that's right about 0 over here. Went straight through. You saw I slid the ruler underneath the shark. 23.5. Boom. So 23 point, well, that's right. Yeah, 5. It's 23 centimeters and 5 millimeters. Echo, what is 23.5 divided by 2.54?
23.5 divided by 2.54 is 9.252.
9.252. 9 point, we're going to do 3. 9.3 inches. Whoosh. An oily book. 9.3 inches, 23.5 centimeters. Righty. Slide that out. We're done with that page. The external anatomy is important to go through because when we're cutting and we're describing something, we'll describe it to those main things, like the eyes, the spherical, the fins, etc. 2 sharps out, 2 sharps back, 1, 2, 3, 4, 5, 6, all sharps are accounted for. Okay, locomotion. Oh, skip right over. Don't want locomotion, I want integumentary. This may be the greasiest shark I've ever worked with. My book's already soaked. Okay, integumentary system. Systems are groups of organs that work together for one purpose. A cell is an individual, cell is an individual functioning structure that's capable of life on its own. Your cells typically don't leave your body, they depend on all the other cells in your body. So a group of different cells working together for one purpose is called a tissue. A group of different tissues working together for one purpose is called an organ. So if I have a muscle cell, boom, working on its own, I have a muscle cell. But if I take a muscle cell plus I take, I'm trying to think of a good example. If I take a chondrocyte cartilage cell that's going to make part of a tendon, we'll say. And I put those two together and they're working together. Now I have a tissue. If I take these different tissues, so if I have a big, sorry, I said that wrong again. If I take a group of muscles, put a bunch of muscle cells together, all one purpose, that's the tissue. But if I also take this group of chondrocytes over here and put them up, or pair them with the group of muscle cells, now I have an organ. So if you think of something like a stomach has a lining in it. That's one type of tissue. It has muscles. It's another type of tissue. It has blood vessels. It's another type of tissue. It has lots of different tissues working together to help you process food. That's one purpose. That's an organ. If I have a group of organs working together for one function, that's an organ system. So if I have my mouth, my larynx, I shouldn't say larynx, sorry. If I have my pharynx, and I have my esophagus and stomach and small intestine and large intestine, all of those things working together to process and digest food, that's an organ system. Integumentary system thinks skin, right? Skin is one organ in that system. Other organs are hair, nails, glands. Those are all organs, right? Individual organs, because they're made up of different tissues inside. The integumentary system of a shark is actually pretty sweet. So you've already figured out it feels like cat tongue if you go backwards, right? If you go forward and feel it, it's pretty smooth. If you go backwards, kind of hear that scratch. It's like nails on a chalkboard. It's because these scale-like structures are special, really special. We call them dermal denticles because the name actually tells you what they are. Placoid scales just mean plaque-like scales that overlap. Denticles are like shingles on a house, not shingles like the painful stuff that people get. So if you look at their shape, you'll have one that overlaps another one that overlaps another one. So in one direction, you would go off this one, whoop, drop into the next one, whoop, drop to the next one, nice and smooth. But if you go backwards, it's uncomfortable. Here they drop off to the next one, you go backwards, not comfortable. We call them denticles because if you look at just the prefix of denticle, what medical profession starts with dent? Dentists, right? What do they work on? Teeth. Denticles are actually teeth. They're little teeth-like structures that cover the shark. So I think of medieval knights and their chain mail. You know, it was the series of rings so that if they got hit sideways with the sword, it was blocked. You know, it wouldn't cut them. It would hurt like crazy, but it wouldn't cut them because of the protective armor. These little tiny microscopic teeth that look like that are actually teeth-like. If you take and dissect a tooth, let's say here's your generic tooth fairy picture tooth, right? You've got the root, you have the enamel on the outside, you have a hollow core in here that we call the pulp, and then you have dentin, which is the strong material that gives it structure. If you take one of these and you split it apart, it has an enamel outside, it has a dentin structure, and it has a pulp in the middle, just like a tooth. If you take a shark tooth apart, it has the same stuff. So a shark is kind of covered with teeth, millions of little tiny teeth everywhere to protect it. So the benefit of having a armor-like skin is that you saw when you tried to put the pin in, if another shark actually bit at it, it would be protected to an extent. Right? Skin color, there's a reason that they're gray, typically gray on the top, white on the bottom, right? If you're a shark and you're only 2 feet long, you're not the biggest fish in the sea. There are a lot of bigger fish. A lot of those bigger fish like to hang out above you. So you find a lot of small fish towards the bottom or things that get eaten towards the bottom. And then more of the predators stay up a little bit higher. Not always the case, but usually. Sharks' predators are usually, not always, but usually outside the water. Like a fish that's 2 feet long or 7 inches long or whatever, a shark, its predator that's going to try and get it is usually like any kind of animal that's sitting out, like a seal that's above the water looking down in. Seals can eat sharks. It happens. Smaller sharks. Birds that fly by, humans that are looking down and in. So if we look at A shark in the ocean, you look deep into the ocean, it's just black because of the absence of light, right? So if a shark is swimming along, you're looking down at it, you're seeing this dark gray skin blending into a dark background, a black background. But if you're the prey that the shark is hunting, shark's mouth is on the bottom, so you know the prey is below them, right? Let's pretend this is the sun, right? You're looking from the ocean bottom out, and the shark's swimming along like this. If you're the prey and you're looking up, you see a light from the sun. You also see the white underside of the shark. It's hard to distinguish the shark. If it were dark, it'd stand out. So this helps it camouflage from its prey. This helps it camouflage from its predators. Shark's design is pretty cool. Maybe one of the perfect killing machines. Other than an owl, owls are sneaky killers. Their flight is silent. They don't make any sound when they fly. It's weird. All right, which is perfect for sneaking up on mice and stuff. All right, so skin color is important. And then there's a link in the book to other things about the skin color that are pretty cool too. All right, so denticles, the skin color has a purpose. Locomotion means movement. There are two systems, muscles and bones, right? Skeleton. No bones in the fish, so it has to be a skeleton. When you look at the muscle, all this dense material is muscle. There's muscle in here. It's a little flabby, but muscle. When you look at the shape of the shark, they're kind of like a torpedo. And the muscles are really strong going along their spine so that it can twist little parts here, not all at one time, but individual sections. A shark doesn't typically use its caudal fin for a propeller. It uses it more like a rudder. It turns. Propeller pushes the boat. A rudder steers the boat. The muscles are kind of like a snake. A snake doesn't have anything that helps it move. It just moves with its muscular body and scales to go across the ground. It wiggles. A shark's the same way. A shark glides along like a plane coasting until it's ready to swim fast, and then it wiggles its whole body, right? Not just the tail. So it propels itself like a torpedo through the water. Slender, moves quick. When we get to the muscle, so we're going to talk about muscle a little bit, but when we get to it, we're not going to dissect all this out here. You can do that later if you want. I'm going to show you how to get into the muscle. First, let's talk about the bones briefly. Right, so if you flip the page, kind of hold this up, you can see the similarity. You can see kind of the outline of where well, maybe if we put it over this way, it'll help you. Kind of see the outline of where the vertebra goes straight down, and then you have the dorsal fin poking up out of it. You can see the shape of the skull, not like ours, so more pointy. It's not made out of bone like ours, so it feels dense, but if I squeezed hard, I'd crack it. Sharks aren't used to having things squeeze them, but it would crack it kind of like an egg squeezing it on the side. You can feel the shape of the skull, so I can feel this part here, right here, right behind the eye sockets. I can feel it dropping in right through here. So here's the neck. I can feel the muscles in the neck. And I can also tell that's neck because look, I can wiggle the skull and hold the neck in place. It doesn't move. So if we made a cut across here, you could actually cut the spinal column, the vertebra, and look at spinal cord. Going down, you can see the vertebra going down, a rib cage. Doesn't go all the way around like ours and wrap. It actually just gives structure or support to the muscle groups that are along here. So our rib cage protects our internal organs, heart, lungs. Shark doesn't have that. If you look and pair us up, 2 arm equivalents, 2 leg equivalents, right? You have a pelvic girdle area. Right? You have like a shoulder girdle, joints that move it. A lot of our structures are very similar. Right. I'm looking for next page, nervous system, and we're going to start cutting in. Boom. So, nervous system, 5 sensations that you have, right? You have smell, sight, touch, taste, hearing. Sharks have 5 plus 2. So, sense of smell. There's the nostril or the nair. If you look in there again, it's closed. It's blind-ended is what they refer to it as. So it doesn't go down and into the mouth like ours does. If you look into the nose, water's designed to go in and then it can squeeze it and flush it back out. Goes in, squeeze it, and flush it back out. So that when it smells something, you, bloodhounds, shark, we all smell the same. So inside the nose, we actually have receptors that detect that. Let's say whatever it is in our environment. Let's say that this pin is made out of food. When I drop this pin into something fluid, like water, or even air, is kind of fluid. If I drop it into the water, particles of the pin will float away. The highest concentration of particles will be closest to the pin, but as it spreads out, I'll have less and less. When a bloodhound smells for a rabbit, it smells the oils and things off the rabbit that touch the grass. Those oils stay there. So as a bloodhound comes along smelling, it'll smell the grass here, 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 and it says there's a high concentration and moves towards it. And then it smells here like this constantly. And it's constantly steering towards the highest concentration. Sharks are the same way. Particles from a drop of blood in a swimming pool up here can drift across, and a shark can smell it all the way in the other end and swim towards the blood to try and find the source. Smell. What's gross, cool gross, is that particles from the blood actually go into the nose, activate the receptors, and then get flushed back out. When you smell something, it's exactly the same. When you're walking along and you step in a pile of dog poo and you smell it, when you take a big whiff of it and you smell the actual poo, it's because particles of that dog poo drifted in the air up into your nose, and now they're in the mucus lining of your nose. So that poo is now in your nose and you're smelling it. You can blow it into a Kleenex and clean that out, or if you don't do that, it'll break free, get into the mucus, and go down into your stomach, and you'll swallow it. You digest it. So you're just really eating dog poo after you smelled it. Ugh. Everything that you smell, particles have to drift into your nose, get activated up in there, and then break free. So next time you're in an elevator and someone goes, and you smell that, ugh, that means part of their poo particles are in your nose. Gross, dude. Okay, that's smell. Sight, so vision, eyeball. Out of all the fish, the shark eyeballs are the most similar to human eyeballs, because if you look at the picture of the human eyeball, one thing is, if you watch a shark attack, when it goes to bite its prey, it blinks. It actually has an eyelid. It has one eyelid that comes up across the bottom to protect its eye. We have two, one on the top, one on the bottom. Most fish don't have eyelids. They have a clear layer over their eye that keeps it moist, but they don't have eyelids to blink. But a shark does. Another thing, in here in the eyeball, you have an iris and a pupil. The pupil can dilate and constrict. Dilate means to open up and get big. Constrict means to squeeze down. But it has a pupil and iris just like people do. So, in other words, the shark can adjust to the light close to the surface of the ocean, but it can also adjust to the darkness down in the deep parts of the ocean. Kind of weird. Which brings me to the last thing about the eyeball. Well, not the last thing, but one other special feature. This is a human eyeball, but there's a wrapper around the back. It's a mirror, really. So it's a biological mirror. It's full of little tiny crystals that have colors to it. So that when light comes into a shark's eye, it goes through the pupil, goes through the lens, goes through the aqueous humor. This is all fluid, like a gel. Hits the back. The shark sees that image, but the light actually hits the mirror and goes back and hits that layer of receptors a second time. So a shark can actually see way better than us in the dark because it's getting at least twice the light sensation. Other animals like cats and dogs and other animals have these too. If you ever see your cat at night and you shine a flashlight in their direction and their eyes glow, it's because this tapetum lucidum, this mirror layer, the light goes in, bounces off that layer, comes back out, triggering vision twice so they see in the dark, but you see this weird color to it. Like my dog, I have a Bouvier, and her eyes at night, if I shine a flashlight, are this red-orange, like evil-looking color. Huge sweetheart, but very scary. I have a friend that has a miniature schnauzer. And when you shine the light to his dog's eyes, it gives like actually kind of like a teal color, like bluish teal, like that. Do it to a cat and it turns out yellow or green. So even though these are dogs, their eyes can be different. Even though the cats are different, their eyes can be different too. Even though they're the same, they can be different. I'm trying to think of a good example. Yeah, that's pretty much it. Humans don't have this reflective layer, but if you shine a really bright light into our eyes, it will hit this back layer. There's a layer of blood vessels back here, and the light bounces off the blood vessels and goes forwards. You might be young enough that you don't remember this, but when I was a kid and you looked at pictures of people that were from a flash camera, that flash gave them something called red eye because the flash was so bright, it went into their eye, hit the back blood vessels, and the light reflected off the blood vessels, and then the camera snapped the image. So you would see red eye from the blood vessels in the back of their eye. Crazy. So now cameras are programmed so that the light travels at a different speed than the actual image for the red eye, or it will block it out. All right, sight. Sharks can see really well in the dark. Better than us, way better. Touch. So sharks are a lot like us. Where are the two most sensitive parts of touch for us? Fingers and mouth. No fingers. So most of their touch sensation is actually around their mouth. This is scary because if you were a baby, where do you put that yellow ball? You put it in your mouth, right? If you were a shark, what would happen to that yellow ball? You're going to bite it, right? It's going to destroy it. So sharks, a lot of times when you hear about shark attacks, it's not because the shark is really intentionally attacking something. It's because it's curious and it wants to know more about it. So to touch that thing, it has to put its mouth on it. But you got 6 rows of teeth here, man. It's going to shred whatever it touches. If you hear about like shark attacks, people on surfboards, it's because one of the favorite meals of a shark is a turtle. So you've got this surfboard, body board, boogie board, and you've got the person's legs poking out of it, and it's kind of like a turtle swimming along to a shark, right? So they take a big bite, and they're like, ugh, that's not turtle, that's human, tastes disgusting. And that's what I hear. I hear humans taste disgusting. That's why a lot of animals like lions don't want to eat us. They kill us because we're a threat, and they just leave us there. Same thing with a shark. Very few shark attacks are actually fatal. They're mostly accidents, and the shark's like, ooh, I don't want that in my mouth, and spits it out. All right, so taste. And then hearing. Oh, sorry, that was touch. On to taste. If you open up the mouth, you can use your scissors or tweezers and pull back. There's the tongue, right? That's where taste is at, right? Just on you, not on a shark. So a shark's tongue is really firm. It's actually a slab of cartilage where yours is a slab of muscle. So we use our tongue, we can stick out our tongue, we can, curl it into a U shape or circle or whatever for some people. We can do lots of things. A shark's tongue is just really a foundation or like a floor. The taste buds are up here in the roof of the mouth. So a shark bites something and then smashes it against the roof of the mouth. It's like, oh, that's not a Snicker bar, right? So another fun fact is a shark can push its stomach out to push things out. So when it vomits, it doesn't just do that. It pushes its stomach out and then sucks it back in. Ugh, there's your gross fact, right? Right, taste. Hearing, that is not an ear. The things that are closest to an ear, there they are right there. I don't know if you can see that little speck. It's a dot, and there's another one right there. 2 little holes. So these tubes let water flow down and circulate around the ear. A shark's ear is kind of like ours, but not at all. So we have an external ear that catches the sound, redirects it down to the middle ear, which amplifies the sound to push it into the inner ear, which is the cochlea, right? Where the cochlea is at. So this external ear catches sound for us. We hear it, we push it in the direction we want. Sharks don't like that. Sharks hear through water pressure changes, right? So the water pressure changes the water in this area. They can feel the vibration through their skull. It shakes the inner ear, the cochlea, and sends the sound signals. what's kind of nice about our hearing is that we hear a lot of frequencies. If you took this cochlea, it looks like a snail. You'll have to look at your book because mine's a mess and the camera's not zooming on it. But if you straighten it out, instead of it being coiled up, it was just straight. It's like a piano keyboard. High pitches at the beginning, low pitches at the end. We have a large frequency of sounds we can hear. We can hear a high-pitched flute. We can hear a low-pitched bass, right? Sharks hear primarily the low-pitched bass, which makes sense because underwater, you don't hear a lot of high-pitched sounds. You hear more of like the muffled, bassy sounds because bass sounds travel further, especially in water that's trying to dampen them. So when you're underwater and you're hearing people at the surface talk, you don't hear the high frequencies, you hear the low bassy sounds. Sharks are the same way. They can hear long distances because bass sounds travel long distances. There are the 5 basic senses. Sharks have 2 more. The first one is pressure. That lateral line that goes along here is actually a series of little tiny organs. They're holes, but they detect water pressure changes. So if a shark swims by you and the water from them swimming bounces off you and comes back, it knows you're there. And it's like, excuse me? You taste bad, I don't want you. So if it's swimming along, it can actually know how far it is away from a rock in the dark, just like a bat does. Bats squeak, sound bounces off the rock and comes back to the bat. Sharks, when they swim, that water pressure moves, bounces off the rock, and then hits that lateral line, and they know how far away it is. If you ever see sharks that are circling, if there's something in the middle and they're moving around, they can feel the water waves bounce off that thing and come back to them, and they can localize where it's at. So they're constantly trying to figure out where this thing is. That's the lateral line, pressure system. And it actually syncs together with hearing, so it's almost like they hear the pressure, which we actually do hear pressures, but it's a long story. Electroreception's the last. This is probably the coolest though. So I don't know if you can see all these little tiny pores. Not the 2 up here that we were talking about, but all kinds of little pores out there. Can you see them on your fish? Lots of little tiny holes. Those holes are also organs. They're called the ampules of Lorenzini, and they're filled with a gel. So a gel that doesn't dissolve in the water. But here's the best example I can give you. If somebody has a heart attack and you see them in the hospital and they have those electrodes hooked up to their chest, you know, they take the sticky gel pad and they stick it on, right? And then they put wires on it. They're using a gel underneath that amplifies an electrical signal to the wires so that we can tell the electricity of their heart. Every muscle in your body actually sends off electricity. Your brain sends off electricity. Your heart sends off electricity. We can detect that with different things. These little sensors are exactly the same. They detect electricity. So they know if a fish is close to them in the dark, and that fish twitches, the electricity off the twitch can be detected by the shark. If the shark attacks the fish, right? And it's struggling to fish to try and kill it, it knows when the fish is dead because remember, the heart's electrical. It knows when the fish quits fighting and it knows when the electricity of the heart stops. So it knows it's killed its prey. Man, sharks, kind of cool, kind of cold, kind of kill things. That's electricity. And a lot of these things, you can Google these pieces of information and find really cool videos out there about them where they do tests and experiments. Right? So there's nervous system part 1. Reproduction is the next one. So if you saw the pre-lab stuff and you looked at it, you can see that sharks reproduce in different ways. They can have eggs and lay them like a chicken, where the egg develops outside the body. So a bull shark is the shark that I was talking about that can swim up the Mississippi River and into the Illinois River. So they can swim up there and they can plant their eggs. Eggs hatch, and there's not a lot of threat to those little sharks because they're mean, nasty little predators, right? But let's say that there's a shark that it's babies, which, do you know what the name for a baby shark is? I made you hum the song in your head, didn't I? So catchy. They're called pups. So they can have the eggs, plant the eggs in seaweed or whatever and hope they're protected. they can make the eggs and they can hatch the eggs inside of them and then let the baby shark pup, whatever, come out the cloaca, which is the hole right here between the pelvic fins. Oh, nuts, I broke a glove. Don't want my hands smelling like fish. So the pup can come out live born, even though it was from an egg, or it can be just like a human. So another way that a shark can reproduce is like a human, where it has a placenta. So the shark is growing inside mom. It's attached to mom until it's ready to be born, and then it's born and swims away. Or, kind of a cool one, you can have something called intrauterine cannibalism. So the sharks are actually, like babies growing inside mom, 50 on this side, 50 on this side. But as soon as the biggest shark hits 4 inches in there, that shark will eat the other 49 of its siblings. Boop, 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 boop. It eats it. This one eats the other 49 of its siblings. And then when it's ready to be born, you actually only have 2 baby sharks. That's it. There were 100 developing, but only 2 made it because the biggest sharks ate the other ones right inside of mom. What are you kids doing in there? Quit fighting. Quit fighting. Don't you eat your brother. Kidding. Anyway. Oh, man. If I were a shark, my brother would have been eaten a long time ago. Before he was bigger than me. So anywho, those are the ways they reproduce. The hole back here, if you caught it, was called a cloaca, and a chicken has the same thing. So a chicken can lay an egg out of the cloaca, and the cloaca is one common output for urine, feces, reproduction, and also salts, which we'll get to later. I'm going to replace my glove real quick. Okay, so that's the cloaca. But it's really cool looking up the different ways that sharks reproduce. It's amazing because I mean, like all humans reproduce exactly the same. All cats reproduce exactly the same. But sharks can do all those different methods of reproduction. It's so weird. Okay. Next page. Now we're going to get cutting inside of respiration. So the respiratory system. Gills instead of lungs. When a shark needs to breathe, it has to push water over the gills. It doesn't have a device like a bony fish that can flop and constantly recirculate water. So sharks need to move most of the time. If they have the spiracle, which not all sharks have, but if they have the spiracle, like I said, they can suck water into their cheek, squeeze the cheek, and blow it out the gill. So they can actually just keep puffing it. Again, if you can Google an image or a video of it, it's weird because it's like they're going, oh my gosh. They're sitting there pulling in water, flushing it over. It's like they're having an asthma attack or something underwater, but they're actually comfortable in breathing. If you look at the number of gills, there's 1, 2, 3, 4, 5 on mine, 5 on the other side. Most sharks have 5. One exception is the 7-gilled shark, and I kid you not, that's its name, the 7-gilled shark. Wonder how they came up with that one. Yeah, it has 7 gills. Okay, let's get in there. So now let's look at the pathway. Excuse me. So how we're going to cut. This is exactly how we're going to cut. It's medical terminology. To do it properly, you can see the red dotted line just to give you a hint. But when we're cutting, we're going to cut on the left lateral side. So not medial, lateral, left side. Shark's left. The shark is your patient. It's their left. Here's my left hand. Here's the shark's left side. So we're going down the left side. We're going to go medial to the gills. It says medial to the gills. So this side of the gills. Don't cut through the gills. Try to stay on this side of the gills. And we're going to go all the way down here to what would be the shoulder. And it's described as stopping at the most cranial, towards the head, proximal, close to the body, corner of the left pectoral fin. So the cut is going to come from the mouth on the left corner, staying close to the midline of the body around the gills, and we're going to stop right there at the shoulder. All right. I'm going to flip my shark around because I'm right-handed, and it's better. The best way to do it is to slide the scissors in and bite with this part here for leverage. And I wish I didn't have this because I'm afraid I'm going to stick my sharp, pointy scissors into something I don't want to cut. So if we open this up, and you can put your tweezers in there. to hold the mouth open. I'm going down here. I'm looking for the corner of the mouth. There's the corner. It's crazy to think that's not bone that's making the jaw. It's all cartilage. We're going to see that in a second. So I'm wiggling, and then I take a little bite, little bite, little bite, little bite. For real, little bites. Because the shark's skin, remember, is like teeth. It's a hard armor. In fact, they used to use shark skin to polish things like sandpaper because it's smooth, but it's very, very aggressive for fine polishing, like polishing diamonds and rubies and gems or wood or whatever. But it can really get in there. The enamel stays hard and you smooth things over. All right, so I just cut. Remember, I missed the gills. I cut right above it. Here are the gills. Oops, I guess I didn't finish that cut. That's what I want. I went right there to the shoulder. Boom. When I started cutting, I cut kind of light, closer, superficial to the surface because down here is the mouth and it's passageway and I don't need that. I just want to see these gills. Here's a gill rake. It looks kind of like teeth. It's not. It's a gill rake. The gill rake is so that if they swallow shrimp or they swallow something, it's not going to follow the water out the gills. It will be redirected and go down into the stomach. The gill rake's there to keep like the shrimp or a little tiny fish from getting stuck in their gills. That would be like you shoving a minnow up your nose. It wouldn't be very comfortable, right? Well, actually, it'd be like you shoving a minnow up your nose and making it all the way to the lungs because it's lodged in their lungs. If you look at the gills themselves, kind of a cool design. I don't know how clear you can see that, but probably not very. But it's like leaves or pages in a book, the way that they overlap. So that water has to flow in between every page, and the gills are full of blood vessels. So as the water passes by, the oxygen leaves the water and goes sucked into the gill, into the blood, and to the rest of the body. There's actually a picture of it on the next page. We'll come back. We'll make that other cut in just a minute. So you can see they either bring it through the spherical, through the mouth, it goes over the gills. We have to bring it down in our nose. We hold our breath for a part of a second, let the oxygen get into our lung tissue and go off into our blood vessels. You can see the blood vessels. Fish can't do that. They have to bring the water constantly flowing over because they can't hold the water on the gill to pull the oxygen out. It has to keep moving. So as we cut down, you'll see those little pages. This is awesome too. If we flip one more page, kind of moving right through. When you see red blood in a picture, it means it's oxygenated, lots of oxygen. When you see the blue, it doesn't mean that the blood's actually blue. They do that because the veins, the reflection of light off the veins looks a little bit blue, and veins are typically without oxygen. But the blood itself, when it has oxygen, is bright red. When it doesn't have oxygen, it's more like a wine color, like a dark red color. So when it's bright red, plenty of oxygen. Dark red, not so much oxygen. Here are the gills. Think about this. So I'm going to the market to buy a fish. And when I get there, I want to know that my fish is fresh. So I take the gills, I pull back the bone, look in the gills. What color should they be if they're very, very fresh? Should they be blue, dark red, or bright red? If you have a fresh fish, they're a bright red color because there's so much blood circulating through the gills. It looks bright red, kind of like that. It's never going to be blue, right? It shouldn't be blue. But if that fish has been in the market and out of water for days, it'll be a dark red because all the oxygen actually escaped back into the air or is broken down and moved along. So if you buy a fish that has dark red fin or gills, don't buy it. Go for the ones that are fresh red. There's your, hey, parents, actually, when you go out shopping for fish, let's take a peek at those gills. You look like a genius. All right, so there you can see the gills. We saw the gill rake that prevents. Where you cut through here, the jaw, you feel that's not bone, that's jaw, and it's actually cartilage. what's kind of cool about the cartilage is that it's kind of translucent. You can see through it. So if I put something behind it, I can actually see the outline of the scissors as they move back and forth. Whoops, sorry, like this. There's the cartilage. There's the tongue. You know what? I've never cut the tongue before, but my curiosity has the best of me. I'm going to cut the tongue. Look at it. Yep. See the cartilage? A lot of cartilage in there. Firm. Not muscular like our tongue. You can see all the lines on the gills again going across. See all those fine lines? Yeah, I gotta get a camera that focuses better. All right, but now we're down. We're gonna cut open the chest. We're gonna look inside, look at the heart. So I've already inspected the gills. You can see the pathway of fluid going across. Actually, before we do that, grab your probe. Take the dull end of your probe, stick it in the spiracle like we were talking about before. So stick it in there and see where it comes out. So you can see the spiracle allows water to flow in, get into the mouth. They puff up the mouth and then go push it out, push the water over. It's like a valve pump, right? Water goes in, trapped, water goes out. Doesn't go back out the spiracle, goes in, close the spherical valve, and then push back out. Coincidentally, that's the same way that the heart pumps blood. So let's look at the heart. So respiration, the respiratory system, which is the lungs and the airway, and lost my scissors, and the cardiovascular system are technically both combined to be the circulatory system because you're trying to circulate things through the body. You're circulating air into the lungs, oxygen gets into the blood and then moves it along. So we're going to look at the rest of our cardiovascular. Right? I'm going to do something that's not in the book, but I'm going to show you how you can skin a shark. You can actually skin anything like this, but every organ in the body has a wrapper. Your brain has a wrapper. It's called the meninges. If you do the stem where we cut the internal organs, you'll get a brain that has the meninges on it, and we'll actually cut it open. You'll feel it and everything. But the meninges protects the brain. If you get an itis of any of these sacs that wrap around organs, it's called a something-itis, right? Inflammation. So if you get swelling around the meninges, it's called what? Meningitis, right? Around the lungs, we have a pleural sac. So swelling of that would be called pleuritis. Around in the stomach, all the internal organs, we have peritoneum, so it would be peritonitis. Okay, there's always a wrapper. The skin is a wrapper, but the muscles have wrappers around them too. So if you're eating chicken that's been cooked, you can peel the muscle groups off and the muscles stay together because that wrapper kept them intact like a hot dog or a sausage just stuck together. We're gonna go in and try and peel a little skin off real quick. We got a couple minutes. So I'm gonna find, there you go. I just cut a little spot open. I can see some of the muscle underneath right here, and there's the skin. I'm closing my scissors and I'm wiggling them. Wiggle, 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 just under the skin. I'm not stabbing. I'm wiggling it, and I'm gonna open them, pull them out. Wiggle into that hole, open, pull out. Wiggle into that hole, open, pull out. So this drives me crazy. I love the students over at the med school, but they're going to be doctors, and so they think, cool, I'm going to have a scalpel and I'm going to cut things. But in reality, scalpels, they're really sharp, but they cut things you don't want to cut. So most surgeons will use a scalpel to get into the skin like this, but once they're in, they take a pair of scissors just like this, slide it under the skin or between the organs they want to isolate, and they open it up. It's called blunt dissection. So I can open it and do this, and you can see where my scissors are going just under the skin, separating, separating. Your fingers will do the same. Once you have a good pocket in there, you can slide your fingers under. This is also blunt dissection, and just wiggle them. Wiggle, 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 wiggle. Wiggle, wiggle, wiggle. And this is actually how I prefer separating organs. Just once I get in there, use my finger. I'm separating all over the place. My finger going down. You can kind of see the muscle patterns underneath here. I'm just separating. And on a creature that hasn't been preserved, this actually goes a lot faster, but the preservative changes the proteins that hold everything together and actually makes them firm. It's kind of like cooking an egg. If you have an egg, the clear part's called albumin, but when you cook it, it turns white and it's not liquidy anymore. It's firm the same way. Okay, so I've actually dissected way down and way up. And if I wanted to, I can make that cut across like it shows. So it showed cutting from the top of this fin to the top of this fin. When I say show, I meant right here. So it says cut transverse from the proximal cranial corner of the pectoral fin to the proximal cranial corner of the other pectoral fin. That's what I'm going to do. I'm going to cut across. Shoop, shoop, shoop. How easy that cut. Amazing. And this isn't in the cuts, but because I separated all that, I can actually take my scissors, cut up, and now I can see the muscle groups. So there's the chest area, muscles. I can see the fins up here, or fins, sorry, gills up here on both sides. I can see the muscle fibers. And when you look at muscle fibers like this, I can see it, but I don't know if you can. They're little tiny lines, kind of like the gills look. The lines go straight in this direction. That means when this muscle moves, it will always pull this side closer to this side. So this muscle must be for either retracting the jaw like this or pulling the whole head down, because they only move in one way. If I want to move another way, I have to have a whole other set of muscles to move in that direction. But look at that. You can see all the muscle. And if you didn't cut this far down, don't worry about it. I can open this up and I can see the muscles underneath. And I can see the muscle wrapper, the fascia that's protecting it. If I want to go underneath that fascia and look at the muscle itself, I would have to take a knife or something and cut it open like this. So you can see the fascia starting to peel. Now I would go under, and because this has been cooked in chemicals, just like formalin, if you put a raw egg in a bowl of acid, it would actually turn white because it's getting cooked, but not by temperature, by chemicals. That's what's happened to all the structures in the fish, is that the tissues were cooked by chemical preservatives. All right, so we're across. You can explore that later. You can peel your whole shark apart later if you wanted to. And then you've got some nice sandpaper, right? You can polish up your rings. Very nice. All right, I've opened this up. I want to cut through the muscle. Aim high. If you feel here, it squishes in. Keep feeling, boom, there's a breastbone. It's not a bone, remember, it's cartilage, but this is the same as your sternum, which is the bone that goes in the center of your chest. We want to get back here where the heart's going to be. If we go down here, there's a good chance we'll hit the abdominal region. Just like on you, the bottom of your rib cage, below it's your abdomen. If you poked into there, you'd see guts, right? If you cut into a rib, which is above the bottom of the rib line, you'd see lungs and heart. That's what we're doing. We're shooting for above. We want to actually cut that sternum in half. Because of the way I dissected, I can push into this side and snip. I'm right-handed, so it just made it handy. See that? Cutting right across. I felt the snap of the breastbone, sternum. I use a lot of the layperson names, but I also will tell you the technical names. And I can already see my heart. There it is, right? So I'm going to keep going back here and finish this cut that I started before so I can open this up like a book. Right, I'm over here, snip. Just going to cut, cut, cut. Yeah, very nice. And there's our heart. You can feel right here. You can feel there's a sac along the bottom. That would be I should look it up. I don't know if that's the diaphragm in a shark, because the diaphragm in you helps you with breathing. It moves your lungs, and it separates your thoracic cavity, where your heart and lungs are, from your abdominal cavity, where all the other guts are at. So I can feel there's a muscle or a membrane right here that separates this chest from everything else. Dang, I'm gonna have to look it up. I'm still learning. I like it. When I was in school, in grade school and high school, I never dissected a single animal ever. We were supposed to dissect worms. When I was in 8th grade, I was sick. In high school, I'm sure we had to dissect something, and I wasn't there in biology class. I went to Metamora, and Mr. Bill was my biology teacher, and he taught me the absolute wrong thing to ever learn about blood vessels. He said veins always carry blood without oxygen. Arteries always carry oxygen-rich blood. It's not true at all. And if you go to med school and you took a test from me, or if you took any test from me, I would put that on there because I want to catch you. The blood vessel with the most oxygen in it in the entire body is actually a vein. It's called the pulmonary vein because it comes from the lungs with fresh oxygen and goes into the heart. In fact, I'm giving you some time, buying some time to open this up. You just want to be able to open it like a book. If you want to cut more, you can. I took the heart. I see the blood vessel coming out, and I don't want to cut that. I kind of like following them along, but it's up to you. If you want to snip, snip, snip so it looks just like the book, go for it. I don't know if I gave props, but man, Nicole, I wrote all the book words down, and she made this thing so pretty. And pictures like this, Eric O works in our media department, or sorry, our like graphic design stuff department, and like a day he drew this. Blows my mind. He drew that. The other day I asked him to draw a picture of the heart on the inside for the next book that we have. Whipped it together in an afternoon. Love it. Wish I had that skill. Okay, so now it looks more like this. Chest open. That's the heart in the picture. It's stuck over here to the more ventral side, which means the front of the shark, where mine is still attached to the dorsal part of that cavity or that pocket. I'm flipping here, whoops. I'm flipping here because of these two pictures. So here is your circulatory system for blood, right? Here's your heart. We got a human heart here, and there are 4 chambers. There's actually 2 sides. When you're developing, you have these 2 hearts that are like in a row, and as you start developing, your heart works together. They bend and they sit next to each other, and they work in perfect sync. So you got one that the top squeezes down, and then the bottom. Top, bottom. But now they're working together. So the top squeeze, the bottom squeeze. Top squeeze, bottom squeeze. 4 chambers. Tops, bottoms. On your right side, your right, on the top you have an atria. This is where the blood comes in. So here's your whole body. We'll say that this is a muscle in your arm, your bicep. You're working hard and you're burning the oxygen up in the bicep. The blood comes back into your circulation, no oxygen, or very little actually, comes up into the heart, into the atria, the first chamber. It's called the atria, that top chamber. Then it goes down to the bottom chamber, the ventricle. This is the bigger, more strong one down here. Atria, ventricle. The ventricle squeezes hard. The atria closes a door so that the blood can't fly backwards, and then the blood squirts up, goes into the lungs, picks up oxygen. So we breathe in oxygen, we hold our breath, like I said, for a portion of a second. The oxygen jumps into these blood vessels, turning the blue blood, quote unquote, into red blood. The bright red blood circulates back to your heart on the other side, into the atria, down through the door to the ventricle, and then the ventricle squeezes hard and pushes it out to the rest of the body. Back to the muscle, gives it some more oxygen so you can do another curl, back up. 2 atria, 2 ventricles. Here's a shark. Blood comes from the body, all used up, goes into a sinus that actually has a big like cone area called the sinus venosus, which when you learn other languages, a lot of languages, they flip the words. So if instead of saying a venous sinus, it's a sinus from the veins, they would say sinus venosus. They just flip the words. Right? So here it collects the blood from a bunch of blood vessels, dumps it into the atria. The shark's heart is actually kind of S-shaped. We'll see that when we take the heart out. Goes from the atria to the ventricle. The ventricle squeezes into a cone that's just the opposite of a sinus, called the conus arteriosus. artery cone. And go figure. And then that cone pushes it out. So this replicates the right side of your heart. Pushes it out to the gills pick up oxygen and then push onto all the other tissues. There's no second side of the heart to push. So what does it, what helps with pushing along are actually when the gills will squeeze, the muscles around the gills, when the shark's muscles in its body squeeze, when the shark's moving and wiggling, all those things are helping to push the blood back to the muscle, drop off oxygen and bring it back. Circulatory system, always in a circle. It's fast and it's efficient, works by blood vessels. So let's cut the heart out. It's just fun saying that. All right, if I pull this down, oh, you can actually see that membrane. There's that pale membrane. Move this up a little bit because I want to see everything. There's that pale membrane going up. I'm going to go underneath it actually, if I can. That pale membrane, I was a little bit wrong. It's not just a membrane. That's part of the conus. Oh, not conus, sinus. See when I push that? I don't know if you can see the little air bubbles. If I get underneath it, I can see air bubbles. That means that is a blood vessel. So that blood vessel is all tied in that membrane. I want to cut that blood vessel. So I'm going to be very careful. I'm feeling under it. I can feel I'm under that pocket. I can see my scissors right through there. I'm just going to go in like this. Take the same path. I know it's clear because I just stuck my scissors in, and I'm going to snip that path apart. Cool. Right. There's a little bit more right here. Got it. Got it. Now I should be able to take my tweezers and pick up my heart. Oh, a little more vessel on that side. There's another one coming in right there. See it? So this sinus is where something collects. In this situation, it's where blood collects. Still didn't get it all. Okay. I have to do some fancy maneuvering here. There's the vessel. Snip. Cool. So now I've separated the entire bottom of the heart. It's free. And lift it up. You see the cavity there. So there was a wrapper around the heart. It was with that conus and that membrane, all of that. It wraps around. If you come in for a stem and we do hearts, you'll actually see the membrane on the hearts. Oh yeah. Actually, the other one that we're sending home still has the membrane around it. It's funny. My boss said, because her daughter likes doing these things, and so she had a kit for the new set. And her daughter said, "Hey, you didn't send a heart with this kit." And she showed me a picture, and I said, "Actually, see that sac there? The heart's hiding in it." Right. So now, heart's still connected. Here's the big blood vessel coming out. So that's the conus arteriosus right there. This goes into one of the most famous blood vessels in the body. It's called an aorta. Right. So this aorta is actually sitting close to the front. So we're going to give it another name. It's called the ventral aorta because it's technically on the ventral side. And there's another aorta that runs on the back called the dorsal aorta. But if we look at the blood, this is kind of cool how it works. Let me get this all out of view. When the heart squeezes, here's the, whoops, sorry. I'm trying to show the pictures here at the same time. When the heart squeezes, there's the ventricle that's doing the pumping. It's going to push out. You're going to see, here's the heart. There's the conus arteriosus, the cone-shaped structure. You can kind of see the outline of it right here. The conus comes out. Come on. And there's your ventral aorta that goes up, carrying what? Oxygen rich or oxygen poor? Blue in a picture, so it's oxygen poor. It splits off into all these little branches, and we call them the afferent branchial arteries. So they're branching. Afferent is telling you they're going at a special organ. So A for afferent goes at the organ, and the organ is the gills. You have to kind of think three-dimensionally. Actually, we'll go over here. So path goes this way, which would come into these. Here's where the vessels are broken. Let's say we go through the ventral aorta. We go up to the afferent branchials. Boom. We go into the gills and the capillary. So remember, this is the right side of the shark now. So This is coming in the front, going into these, picking up oxygen, making these a bright red blood, coming back. These are the efferent branchioles. They're branches, but they're exiting the organ of interest. They're going into another big blood vessel. This was the ventral aorta, so this is the dorsal aorta because it sits at the back. You can see some of these branches will go up. These will go up into the brain. The brain's interesting because water will flow over the brain and also provide oxygen, but it depends on this blood flow too for extra. Right? And then this dorsal aorta has fresh oxygenated blood that will carry down into the abdomen. So we just listed off all of those, whether you realized it or not. So let's take the heart out, kind of a fun thing. And it's so cool looking at stuff like that thin membrane through here that goes around the heart. It's called the pericardial membrane. You can see the gills on the other side of it. Man, I don't know if you can see those, but I can actually see it so thin and transparent. All right, I'm picking up the heart. And my goal is I'm going to cut it as high as I can on the ventral aorta. So let's move this around a little bit. And I'm cutting way up there. I can actually see where it's going to split. So I'm going to cut at the split. Snip. Didn't quite get it all. So I'll cut a little bit lower. Snip. And I had just seen, before I cut it, I'm pushing on this and I can see little bubbles coming out. There's a blood vessel and I can see the hollow center. Pushing down here, I can feel a blood vessel right there. I think we're completely, nope, not completely. Snip, there it is. Boom. Shark heart. So in the picture, it shows it going straight, going straight through the heart. Not so much. So blood comes up here and this, oops, sorry, into this venous sinus. It goes into the atria, which is this flappy sac. Keep moving. It's all flappy because the atria is small and thin. Then it goes from the atria back here down and into the ventricle, which is this massive, kind of harder, more firm area. I can actually see all the little tiny blood vessels going to the surface of the heart, keeping the heart alive. If these blood vessels get broken, these are called the coronary arteries. If these get broken or blocked with like clots, that's when a heart attack happens. So Papa Shark's swimming right along. He goes, oh, because he has a coronary blockage, right? He should have backed off and not eaten all the junk food for years. Quit eating surfers. They're bad for you. They stick between your teeth. All right, so the blood's down in the ventricle squeezes like this, and it squirts the blood into this conus arteriosus, pushes into the aorta, which was the ventral aorta, pushes up, and you can see here's a split here going that way, and then a couple smaller splits going over this way. Let's cut that thing open. I want to see inside. So I'm a huge fan of going backwards. I like to reverse engineer. Take my toys apart, figure out what's wrong with them, then put them back together. Snip. So I'm going right down the aorta. Snip, snip. Snip, snip. Wow, I can really see the blood vessels on the surface. Oh, sorry. Too busy staring. So I started here. I went into the top of the aorta. I snipped, I snipped, I snipped. I'm coming around, snip, 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 snip. And now I should be opened. Yeah. All right, so here we're at the front. Let's open it up book style. Cool. You can see the inside of the ventricle. See it in there, the pocket? I can see the pathway. I'm gonna grab a pen. So I can see the pathway where blood leaves through the aorta, goes up this way, and then blasts out the top. I can see, if I open this back up, I'm getting dangerous here playing with pens this close to my finger. See that hole right there? That's where the atria is at. So if I follow this backwards, I'm not gonna put a pen in it, put the pen back in, stick it back in the pad. I'm gonna put this in there. It's a little bit bigger, but I think it'll fit. There's the hole again, sliding it in. Boom. Now I can feel it. I can feel where the path of blood would come from. See it right there? That's the atria. It comes down into the ventricle, and then the ventricle, when it squeezes, pushes it up. This is kind of flip-flopped. Should be in here. There we go. So it follows the path of the wood stick down from the atria, ventricle, and then follows the metal pen from the ventricle out to the aorta. Pretty cool. All right, I have a pin, so I'm going to count that one, stick it back in. That should give me all 6 of my sharps back. My heart, I'll stick it here. 1, 2, 3, 4, 5, 6 sharps. Sharp pins, my scissors. Oops. And my probe. All right. And then you can actually match these up with the letters if you want to sometime, but you can follow the pathway. Remember, the afferents, ventral aorta comes out, afferents go into the gills, efferents leave the gills, and then the dorsal aorta. Right. Digestive system, getting close to the end, yikes. All right, you already played with the teeth, count the number of rows. Teeth and skin, very much the same. Teeth are bigger, sharper, pointier. They don't get cavities. If they get a loose tooth, it pops out, and one of the back row teeth slide up into the place. They just rotate through. Crazy. We're going to follow this down. So there's the tongue. There's the food passageway. Oh, there's something in there. Here was the chest. So we're going to actually cut over here again. I'm going to make a little snippety snip. Scissors are where I left them. So I want to follow. It's rough. If I bring my finger up here, somebody already said it, but it's kind of like a cat tongue. So that things that go in don't want to easily come back out. So I'm just going to cut across the gills. I'll look down in there. Look at that. There's the esophagus. This is all gunk that we can get rid of. This is all part of the last meal. I don't know if you can see all that. Just taking my fingers in, pulling it out. Ugh. So this is what should happen to food. It eats the food. It goes down and into the stomach. And then the stomach's job is to smash and grind. Like when you eat an apple, you take a chunk, you bite into little chunks, chew it into littler chunks, you swallow it. It's not done yet. When it gets in your stomach, then your stomach has to grind it and turn it into applesauce. Not even the grainy applesauce. It has to turn into something that's like baby food, like this. Gross. Whew. This one must have vomited because its esophagus is kind of turned inside out. There's more of that. You can see the esophagus right there. See all these, it's like fingers coming up at you. So that once the food gets down in there, those little fingers help hold it in place. You can see the ridges on the back that are like fingerprints. Those ridges are full of taste buds because remember, when it eats and tastes, it doesn't taste with its tongue like you. This tongue is actually cartilage that forces the food up against the roof of the mouth for flavor. So when a shark tastes something, it has to actually take a good bite of it. There's a spiracle. There's the other spiracle. Now we're going to cut the abdomen open. There's an image. Oops. We just flipped away from the image. So right here, you can see the dotted line. If you cut right down the, this is called mid-sagittal. Sagittal going right down the belly, almost like it was designed with that line for you to cut. Mid means right in the middle of it. So I'm going to cut, snip. I can feel bone, or sorry, cartilage, snip. I'm putting scissors in because now I'm in the abdomen. Putting the scissors in, pulling it up because I don't want to cut any organs. And I'm just snipping, constantly pulling it up like I'm actually holding the shark with the scissors and snipping. Snip, 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 snip. Hearing my scissors get dull with every cut because of that sandpaper skin. Snip, 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 snip. Coming on down. Going all the way down to the cloaca, the little hole down here. And it's going to get hard to cut right around here because here are the pelvic fins, which is like the hip, remember? So you actually have pelvic bone-like structures here that connect. Our pubic bones are in the front of our hip, and they connect through a little thing called the pubic symphysis, which is actually cartilage. So we're going to cut through that cartilage. Snip. Ooh, that's tough. There we go. I felt it pop. And there's the cartilage. You kind of see it there. So where there's a ring that comes around here and holds the fins in place like a hip, that's what you cut through. This is not in the book to cut, but I'm going to follow that cartilage right above it, so superior to it, and I'm cutting. Yeah, wow. This might be the last trip for these scissors. The skin's really dulling them fast. So I cut right above it and cut over to the side. Still doing it. Cut, cut. I'm going to do the same thing over here. Wow, that's tough. If you hit the like pubic bone region, it's hard to cut through. So if you can get right above it, geez Louise, tough. There we go. When I open this up, it's kind of cool. I can see the layers. Here's the skin. Here are the layers of abdominal muscles, just like we have. The sac, the shiny part, is the sac that goes around all the internal organs. It's called the peritoneum. As I pull back, I can kind of see the skin and all the connective tissue that holds it together. I can see the different layers of muscle. It's crazy. Here, it's kind of pulling the peritoneum off, but not completely. But if you want later, you can separate these. You can see the muscles. You can see the direction of the muscles. See them over here. You can see the layers. You can see a blood vessel there. See it right there? There's a blood vessel. There's another blood vessel. So these are actually called the lateral vessels. There's one here and one here because this one sits on this side. I just didn't cut it down the center very perfectly. So the center line would have been right here where they're both equally distant from the middle. So if you want, you can see that blood vessel. If you wanted to, you probably cut the blood vessel out, but not right now. And you can see that it goes all the way back up to the heart. So this is called the lateral vein, actually. It's returning blood that's been used down here all the way back up into that sinus venosus to go into the heart. All right. I'm going to make 2 more cuts like this one down here, right underneath the pectoral fins. Oops. I'm going to make a cut over. I'm not cutting the fin. Okay. And right here, I'm going to make a cut over. And now I can open this up like a book. And if the chest is in the way, I'll just cut into the tissue here. Oops. So I can open it all up. And I will pin it open like this. Take a pin, stick it there. Take a pin, stick here. Take a pin, stick here. Take this pin, stick here. Oh, that one keeps popping out. Well, if it keeps popping out, I'll just grab another place. Better. Boom. Open it up. Ink. Right? Organs. So we just saw in the mouth, we saw the esophagus. If you want to take the blunt side of your probe, kind of wiggle it in. Feel it here. I'm pulling this back because I think it was going to vomit. Remember how I told you that sharks can actually turn their stomach inside out to vomit? I think it was in the process of vomiting when it died. It's like, oh, never mind, I'm dead. Pop that open a little bit more. All right. So this is in the mouth. I'm going to try and find that down in here. The first organs you're going to move out of the way are these big, they look like, I don't know, eels or something. They're not eels. They're the liver. So here's the left lobe of the liver. I'll pull over to the side. Here's the right lobe of the liver. and the middle lobe right here, this guy. If you look at us, oh, wow, that's really slimy. Here's our liver. Ours goes more sideways across. The shark's goes lengthwise. So we have two lobes. We have a left and a right. We have a little green thing hanging there called the gallbladder. See if you can find the gallbladder. The left lobe, there's a right lobe. There's the gallbladder. It's usually pretty green. In fact, it leaks the green and stains the things around it. So sometimes you'll see, yep, like that, a green line over here on the right side, but no green line on the left side. There's that vessel again, you can see it coming down. So the gallbladder stores, it doesn't make it, but it stores something called bile that helps you to process fats. So when you eat fatty foods, bile is made in the liver, stored in the gallbladder, and when you eat, it's squished down this tube. See it? The tube. It's called the bile duct. Goes down here, and then goes down to the intestines to help you process food, which we'll come back to. So this little organ is called the gallbladder, and it makes bile. Here's the liver. Liver does lots of things. Liver cleans up toxins. So if you eat food that's full of bacteria and germs and chemicals that are bad for you, your liver will clean those out and get rid of them for you. Push it back into the GI tract and dispose of it. Your liver, before you're born, makes blood for you. This little organ down here is called a spleen. The liver and spleen, before you're born, make your blood. After you're born, it destroys your blood. So a red blood cell can only stay alive. A red blood cell can only be used for about 120 days, so 4 months. After 120 days, your liver or your spleen will destroy the red blood cells. Liver and spleen also have white blood cells, which are your immune system. So as the blood goes through, it gets cleaned. Stores in a shark, it stores oils because a shark can't float. I don't know if I mentioned that earlier. I don't think it did. Because in a normal fish, you'll see a big air sac through here. It's called a float bladder. And that air sac helps them float. Sharks don't have it. So if they stop swimming, they start dropping to the bottom. However, if they have enough oils in here, they'll kind of float. It's like water and oil. Oil floats on water, so it'll help the shark float a little bit. But if it stops, it's still going to sink. All right, let's move these out of the way. So I just pulled the liver back. Liver back. There we are. Now I'm going to find out where this probe is going. It's either going to go into this thing or this thing. So I'm going to wiggle it down. Oh, I can already feel it's right here. So mine's in this sac. Right? This sac or line, I'm going to cut open. So find this. If you're not sure if you have the right one, it's kind of muscly feeling. This is not muscly feeling. It's muscly. It feels like a straw if you have a plastic straw and you roll it. It comes way down here. This doesn't. So this is stomach esophagus. Esophagus is what you swallow with. I'm going to pinch it in half and cut into it right in here. I really dulled my scissors. Okay, so I cut into it a little bit. I'll cut further. I cut about halfway through it. Now I can open it up and take a peek in there. You might have a big lump in here, so there might be fish or shrimp. One time I opened this up and I had two fish and a shrimp. And the shrimp was like 8 inches long, curled up. Like, I've been eating, I give up. And then it just curled up into a ball. Right? Next thing I did is I went inside that hole I just cut and I cut up. Don't cut the liver. I cut up about to the liver. And then I'll do the same thing going down. I'm gonna cut down. Cut down. You can cut down as far as you want, but when you get down here, you're gonna see it turns around and comes back up like a J. So that's what I'll do. I'm just gonna cut down. Cut. And it's mostly muscular up here and dense. So when I open this up, I have more of that gooey stuff. Gross. That's the stomach. See all the lines? When the lines go straight like that, they're called rugae. And rugae allow the stomach to stretch when you're filling it. So if you go to a Chinese buffet and you like to eat a lot of food there, stretches open. When the animal is preserved, it's not stretchy anymore. It's hardened. But it would stretch and stretch and stretch. Mine didn't have a last meal, it looks like. It's sad. If I go up and open, look at that. It's not the same. There's my probe. See the probe right there? It wouldn't stick. Look at the wall of this area. They're not lines. They're the finger-like projections. That's esophagus. So when a fish goes in here, starts moving down, the grip at the back of the mouth, the grip that feels like a cat's tongue back here at the back of its tongue, these little finger-like projections, they all kind of squeeze in and trap so the fish doesn't come back out unless it is pushed back out. So esophagus, stomach comes around to a J, and here in the J, it gets really firm, like muscle. It's because this is a muscle. It's a round muscle called a sphincter. When you eat food or when the shark eats food, the only way you can get the nutrients out of the food is if you process this down to baby food. So it smashes and purees and turns it into mush. Once it's mushy enough, this muscle opens up and lets the food go into the next section, which is the intestine. Here's the intestine. You have a small intestine and a large intestine. So yours, there's a stomach, it dumps down into the small intestine that weaves all over the place. And then it comes down, goes into the large intestine, and out the body. Small intestine absorbs nutrients. So you dump that bile on your food to break it down. You dump chemical enzymes to break it down. Once it's broken down, you get all those good nutrients, the sugars, the proteins, and the fats out of it. What's left is feces. Feces goes into the large intestines, and that sucks water out because we're land animals. It's hard for us to keep water in. You don't feel like that because your body's so good at doing it. But it pulls the water out of the feces until it's the poo that we think about going into the toilet. If you compare, there's the esophagus, stomach. Here's the whole intestine. That's it. There's no small intestine and large intestine. It's just intestine. In fact, it's called spiral intestine. Can you see it? It's like a wasp, how it has the lines on it. So we'll cut this open, just like we did the esophagus up there. Pinch, cut, 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 cut. Now I'll go into it and cut again. Cut, 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 cut. It's hard to pull open because it's not really hollow. See that line? It's called spiral intestine because that spiral is like a corkscrew all the way down. So the food has to twist around in a circle as it passes through, getting processed and then pushed out of the body. No large intestine. If you caught, we have a large intestine to absorb what? Water. To bring water back into our body because we lose water way too fast. We need water. A shark doesn't. A shark's in water. So it doesn't need the large intestine to bring that water out of its poo. So this is more like the small intestine. It pulls out all the nutrients it can, and then whatever's left, it just pushes out the cloaca. So when a shark poos, it's not like a pile of dog poo. It's just splatters in the water that you're about to swim in. Ugh, right? Okay. Another organ is this one. It's really important. See it right there? Kind of hides. Here's the J shape of the stomach. There's the spleen. This little guy is hiding. See if we can get underneath it. Probably not easily. It's right there. It looks a lot like the other tissue around it, but if I break the sac, you can see it's a totally different organ. There. It's the pancreas. So the pancreas is really important for a couple of reasons. It makes chemicals that help you digest food, and that's why it's right here by the small intestine. This cord that comes over, the bile duct, connects up to the same structure that the pancreas connects to, and they both push chemicals into the intestine to digest food. Bile digests fat. The pancreas releases enzymes that digest proteins and sugars. So now you have all three major nutrients covered. There's a little piece of pancreas, not little, it's actually big, that hangs off the back here too and comes down. Not the spleen, that's the spleen over here. The pancreas is hiding right there. See it on my fingers? That's all pancreas too. The other thing the pancreas does besides helps you digest food is it releases a chemical, a hormone called insulin that helps you regulate blood sugar. And if it's not being produced properly or not working properly, then you get diabetes. So that's where the pancreas is really well known. Okay, so there's the pathway. Food comes in, gets smashed by this cartilage tongue. Food's tasted on the roof of the mouth, goes into the esophagus, this way, traps the food so it doesn't go back unless it's intentionally pushed back. The esophagus has papilla, fingers. Food goes down into the stomach. The rugae stretch, wrap around the food and smash it because it's muscle. Pushing it down until it's like baby food, like this paste here. Pushes it up. When it's paste-like, this sphincter, this round muscle, opens up and lets squirts of baby food go into the intestine. The intestine has to spiral it around, right, all the way down. As it's spiraling it down, it's squirted with chemicals that break it down. The good stuff comes into the bloodstream, is carried away, and then the poo exits the cloaca. There's no anus. The cloaca is all of the outputs on the bottom part of the body. That's the GI tract. There's one thing that's left here, this little thing hiding, called the rectal gland. This is kind of like a kidney. It filters salt because a shark swims in salt water, and salt water is actually pretty bad for you. So as it eats a lot of salt, this catches the salt in the blood and then pushes that extra salt out the cloaca and recycles it back into the water. Right? That's what you're looking at. If you move everything out of the way, do you see the sac? This sac connects to the vertebra, comes all the way up. It wraps around the internal organs, right? Goes down, wraps around the inside of the body, comes back around, goes back and wraps around the internal organs again. They're all protected by a sac. This is called the peritoneum. There you see, looks like a blood vessel. Yes, part of a blood vessel going through here. Right. Next, mine was a boy. Pelvic fin, extra part. Pelvic fin, extra part. If you just have a pelvic fin and there's no groove here, you have a girl. So all the way up here, this is the testis, the male reproductive gland. This makes sperm. As the sperm's passed out, it goes down. You can see it's connected right here. And you see that tube? It's kind of coily that runs all along here. This is called the vas deferens. So the vas deferens carries the sperm all the way down here, all the way down, straightens, so it's coiled, but it straightens here and goes straight down and dumps to these. So it dumps into the environment close to the female, and then they go into the female and the sperm go into the female and cause fertilization. If you have a female, you'll have the same pathway, but they're not coiled. It's a straight tube that goes all the way down. And you'll probably have something that's kind of like this, but it probably has a bunch of round like balls all over. Those balls are eggs. So this would be an ovary in the female, and those things developing are the eggs. Right? So when they develop and they grow the babies, if they hatch it internally, or they can push it all the way down and drop it out. Right? But you can see that pathway. In between these two pathways, as I push on this, I can kind of see bubbles going through the tubes. Those are blood vessels. That dorsal aorta is right there. I can see it. going all the way down the center, right in front of the vertebra. So if I nick this, shoop, kind of ran along. I think I just cut the vessel. Nuts. Oh, nope. There we go. So you can see some of the branches of the vessel in there coming down and along. Dorsal aorta, bringing the fresh oxygenated blood down to the other end. There's some of the oil that helps keep the shark floating. So those are all the internal organs. Add them all. Here you can see again, heart in the chest. Here are the liver, lobes, stomach, intestine, rectal gland. Here you can go and fill these in, just for your fun. But like, there's the rostrum. So the nose is rostral. And there's, you can plug those in. The green ones are easy easies. The purples are a little more challenging, like what were those little blood vessels that leave the Q, something aorta, goes out, goes to the gills, comes back fresh oxygenated. You can see the papilla, you can see the rugae, you can see the spiral here. You can see this thing that makes blood. You can see that gland that collects salt. So you can go through and plug them in if you want. And the last part, let's take an eyeball out. So we're going to take an eyeball out and get access to the brain. So the nervous system, we saw the spinal cord, we saw some of the bones. Here you can see where it cut. They cut this so that the blood will come out and it doesn't sit in there and cause problems. But you'll notice, hopefully you'll notice, there's a vertebra. And this, depending on what part of the body, it'll have the fins on it or not. But it'll always have three things. Here you have the actual body itself, this round thing. The body grows. A shark never stops growing. So if you slice this, put it under a microscope, count how many rings deep it is, it tells you how old the shark is. I'm not kidding, like a tree. This hole up here on this side is a spinal cord. You can kind of see a little bit of the mushy spinal cord in here still. Below, so this is the tail and this is the bottom of the tail. Below down here, you can see two holes. One's an artery and the other one's a vein. Okay, so you have an artery and a vein. You have the body of the vertebra, which gives it shape and structure. You have the spinal cord that pokes out just above it right there, in that little tiny hole. And then you can see the muscle groups that are attached. So all these flakes are actually groups of muscle. All right, let's go back up to the eyeball. All right, I'm taking the pins out because I'm going to put everything back together. I have 2 pins already stuck. There's 3, 4, 5, 6 pins. I even have my heart here. I'm going to be courteous to the shark. I don't want to show any disrespect and do dumb things. So I'm going to put the heart back in. I'm the same way with anything that I dissect. Because even though we think, well, you know, people eat sharks or people catch sharks for whatever reason, but we learned from the shark, so I'm showing it respect. Putting everything back in, closing it back up. You can go through later and dissect if you want and look at the muscle groups. You could dissect out these blood vessels. Oops. Like there's the vessel here, there's another vessel, 2 lateral vessels. Just for fun if you want to. I'm going to close this back up. I'm going to flip my shark. We'll look at the eyeball. Both of them are pretty dry. So one of the things that happens, your eye is filled with fluid. It's called vitreous humor that gives it shape, makes it round like a marble. But when you die, fluids start leaking out of your body. So that water leaks out. It's not held in there anymore. And that's why there's so much fluid in the sac with it. And that's why this seems collapsed like a raisin instead of looking like a grape like it should. So the easiest way to get to the eyeball, you can see down here, there's the eyelid. I'm going to go up to the top. The skull is all cartilage. So if I'm cutting, like this. Right, here's the eye socket. That's where the eyeball's at. It's really thin through here, so I can actually aim to go up and cut the sides of the eye socket to remove it. That's what I'm going to do. I'll take this one's not bad, so I'll do this one. All right, so I'll go up here, just make sure it's separate, and I'm going to put my scissors in there. I just pulled it up a little bit. I'm cutting to the back of the eye socket. There's a spherical. Why are my scissors getting? There we go. The back. And I'm going to do the same thing at the front. I'm going above the eye. You can see all those little pores of Lorenzini. It's kind of cool. Sorry, ampullae of Lorenzini. They're little pores for electricity. I just pull back. So now I have the tissue above the eye. I can put my finger in here and I can actually feel the eye socket, the shape, the roundness. And this is how weak it is. If I pull back, I just broke it. So that was part of the skull that I just broke. If you don't want to pull back on it, you can just cut. I'm cutting now. There's a membrane around the eye. This membrane is called the conjunctiva. That conjunctiva, if it gets inflamed, you throw the word itis at the end of it, and they call it conjunctivitis. Most people call it pink eye. So there's the membrane. If I look, there we go. Can you see behind the eye? I can see some muscles. So if you look at this book, and this is kind of one of the cooler things about the eye, you've got 6 muscles. You have one on each side, a left and a right. We call those the laterals. Well, lateral and medial. So they sit laterally to the sides of the eye. This one sits out towards the outside edge of the body laterally. This one would sit closer to the middle because it's all medial. You have a superior and an inferior. So one that goes to the top, one that goes to the bottom. Recta means straight up, straight. So there's straight muscles. But then you also have one that's oblique. It goes at an angle over diagonally. So you have 1, 2, 3, 4, one diagonal here and one diagonal here. This ones to the side are obvious because when you pull on it, it's like a puppet. You pull this side and it turns the eye one way. The other way, up, down, right? But these ones that go crooked actually spin the eyeball a little bit. It rotates it, which we don't think much about, and we don't use that very often unless we're falling, really. But it can give it a little bit of rotation to it. It's pretty cool. So these muscles are what I was getting at. If you're looking back here and it looks kind of pink in color, see the connected structures? Oops. Never fails. Your cheek or eye always itch when you're deep into dissection. Right? Here we go. Here's a muscle here. Here's a muscle right here. You see it? But you can see these individual muscles. The goal with taking the eye out is we want to try and get the eye out with as many of this structure still attached. So peel that back. You can take your tweezers if you want. I'm using my fingers because it gets me closer. And I'm just cutting right around the eyeball. So I'm cutting that conjunctiva and the eyelid on the bottom. Don't want to cut muscles, so I'm really trying to avoid it. Snip. I know it's going to happen. So now really the only thing holding in are those muscles and the optic nerve, which is the nerve that sends the signals to the brain that comes off the eyeball. I'm going to pull just a little bit, not too hard, and I'm not squeezing the eyeball either because it's like a grape. If you squeeze it, it'll pop. Wow, do you see those muscles in there? See them connecting? Right? So I've stretched it out about as far as I'm going to go. I'm going to, actually, first thing I'm going to do is I'm going to cut this flap off. Yeah, it's removed. Now that I can see down in there, I'm going to cut each of those muscles as far as I can, so as proximal as I can to the body. There's another one, snip. There's another one, snip. There's another one, snip. Shooting for 6 snips. Okay, there's some up here on the top. There we go. I miss any over on the side. Yep, right back there. Oops, nope. Take it, yeah. All right. Oop, there's one down there. Snip. Ah, that wasn't a muscle. Snip. And the eye's out. See that one? You see it? See how it's a tube? Looks like a tube? Not a muscle. That is the optic nerve. These other ones are all muscles. See the muscles coming out here? It's a muscle, a muscle, a muscle, a muscle, all muscles. And then the optic nerve. So the eye is a little bit dehydrated. It would be kind of like that. I'm squeezing it a little bit. When we cut into the eye, you don't want to squeeze because if you squeeze, it could pop and it will squirt. So right here, the center, the dark spot, well, I can see it's white now, but that's the pupil. All this coloring around here is the iris. The whitish part is called the sclera, and you can see those on the eye. So the sclera blocks light from coming in anywhere except the pupil. The iris adjusts its shape to open up the pupil. So if you have blue eyes, it's the iris that gives you the blue. When you're in a bright room, you see a lot more of the blue because the iris shrinks down to give you a small pupil. But when you're in a dark room, you barely see any blue because you're trying to open up the pupil and get as much light. One of the cool things I thought was the first time I saw a night vision camera and I looked at myself in it, and my pupils were huge because I was trying to get light from the dark room and the camera could tell, how big my pupil was. That white thing in there is the lens. So normally the lens is like a magnifying glass. Light comes through, the lens bends, it's stretchy, so it's squishy when you're alive. But when you die, it darkens over, it clouds and turns hard. So we'll cut into the lens. Remember, or we'll cut in to get to the lens. When you cut this, I always look for folds. I don't want to stab it. I want to find a fold and cut. Oop, yep, I just punctured it. So there was a crease and I just cut the crease like we did to get into the shark earlier. And now I'll just snip down a little bit, snip down a little bit. All right, I'm gonna snip up a little bit. I'm cutting across. I cut through the cornea, the clear layer across the top. I can open it up, a lot of fluid leaking out. I'm just gonna cut it. We call this clamshelling, so that when you cut something round on both sides, you can actually open it like a clamshell, like this. So I'm opening it up. Stayed pretty intact. Here we go. Wow, that lens is really big. There's the lens. Nice and round. It's like a marble, or it looks kind of like a used jawbreaker, doesn't it? It's hard. It's not normally hard. Usually it's squishy and flexible. When we look in here, you can see that dark line along here. That's the iris. You can see proteins that are broken down. Take those out. Right. And I'm looking for a lot of these nerves. In the very, very back, you have the retina. And the retina has the rods and the cones. Rods work in the dark and in the light. So it's like a black and white picture for you. Cones show you color. But the cones are really limited to one spot. So it's actually better for you to see details of things at night because those colors actually mess with your vision. It seems like it's wrong, but it's very true. You have way, way more, about 10 times more rods than you have cones, and they're spread all over the retina. The cones are only in one spot, and I'm trying to find it. That one spot is lighter in color. Peel that. Hope we didn't accidentally rip it out. No, can cheat a little bit. Where was our optic nerve? Right there. Optic nerve is this little tube going in. So wherever the optic nerve is, Where the optic nerve goes in is actually called the blind spot because there are no rods and no cones. So it's actually blank vision. If you ever make it to one of our stems in class, we play with vision a lot for the neuro stem, and we test your blind spot. And it's weird because you know you can't see, but your eyes are actually seeing in that spot where you can't see. It's so crazy. Right, there it is. So the optic nerve comes in right about where this fold's at, and there's a light colored spot right there. That's where all of the colored cones are. What I think is interesting about that is that I was reading that sharks only see in black and white, but they have cones. So if they can only see black and white, why don't they have all rods, which are the black and white receptor? Why do they need cones? But I think what it is, and I couldn't find what colors they could see, is that like dogs have cones. They can see color, but they're not the same colors as us. If you ever watch dog TV, it's actually a channel. The whole channel is like in weird yellows, greens, and blues because that's what dogs see, those colors, not what we see. Right? And then I can't really see it, but all the dark membrane on the back, that's where the retina and something called choroid is, which is blood vessels. And then the last thing is that reflective layer. So all the way in the back, you have that mirror layer of the tapetum lucidum. Way back here, that lets light bounce off and come back in. All right, that's the eyeball. The last thing you can do is brain. And we're technically out of time, so what I'll do is I'll just show you how to get to the brain, and I'll let you do it if you want to, but then I'll show you how to clean up. So you can clean up on your own, but you don't have to clean up right now. In fact, you can wrap it up and store it for later if you want. But to get to the brain, there are two ways. You either can feel the neck right here, and then cut into the neck like that. So I'm cutting across. I'm going to do this kind of quick. I'm just cutting back and forth across. I'm cutting all the muscle, cutting down, and there's a bone right there. I'm hitting a bone. What do you think that bone is right in the middle? It's the vertebrae. So I'm going to go around that bone like this, if you can see it, and snip. I just cut the vertebra. I can bend this like it's a lobster or a crab, and I'm cracking it open. And right there I see the vertebra. You can see the round disc. And there's the spinal cord. I don't know how well you can see it. I can touch it. Squish, squish, super squishy. Pretty cool. You can take your pin and poke at it. The first time I ever touched the spinal cord, I was doing a surgery on a rabbit, and it had died. But we had to take its brain out to study it, find out why it died. That's right. I was doing a necropsy, but I was not a veterinarian. I was working in a veterinary medicine school. And I shouldn't have done this, but we didn't need the spinal cord. So I took my glove off and I touched it, and it had such a weird feeling. And what it feels like is if you've ever seen Crisco grease, or if you have warm butter sitting on a counter, it's kind of like that. It's like stiff but mushy at the same time. It's just a weird sensation. Right? So that can get down to the vertebra and the spinal cord. And then if you want to get to the brain, you can do that whole skinning thing, going like this. So you can go from this perspective forward. There's the skull, right? So you're going this way. Or you can go above the eye here and come back. There's the skull, and there's where the brain is kept. Here's actually the brain itself. So you can see the olfactory pathway. You can see the olfactory bulb area. You can see a cerebrum, which is small, but that's actually the part of the brain that we do most of our thinking with. On a shark, it's small, but in hunting sharks, it's bigger. It's crazy. So sharks that just feed off the bottom have small cerebrums, but hunters have bigger ones, so they think a lot. Here, you have the brain stem, cerebellum. I was looking down here, and here's the brain stem. We are very similar. Cerebellum for balancing coordination, and then the brain stem is basic life functions like coughing, choking, sneezing, controlling the speed of your heart, controlling your ability to breathe. So you can actually find those different structures in this by going under the skin and doing it like this. Going in, separating, going in, separating. You find that this is kind of easy because the skin is almost directly attached to the skull. You do it over the muscle and it gets a little sticky sometimes. Oops. Once when I look up and my whole hand's in the image. So I wiggled up here, I just kept separating, and then I can go under the skin, cut, like that, and peel. You can see the muscles. It's when the shark winks. I'm kidding. Those muscles go down to the spiracle. And it looks like some of them go down to the jaw, so for helping control chewing, and it probably opens and closes the valve on the spiracle. Okay. Underneath that one, just taking my fingers in, pulling this back. Now I've exposed muscles on top of the skull. I can see the skull. The skull is not white like our skull. It's called a chondric cranium, which means it's a cartilage cranium. And if you look closely, you can see the brain actually in there because it's kind of clear. So you can make the cuts. You can dig down. And a lot of times you can actually split this with your fingers. You don't even need scissors to do it. But I snip a little bit, snip a little bit, snip, snip. And then we can get in. And if we really want to take a shortcut, we can just go across the top. But I just cut the brain, so it's not always the best. See, if I pull like this, there's part of the brain right there. So I took a shortcut, but I damaged the brain at the same time. So you can tell it looks a little bit different than our brain. And you can do the same thing. You can go right above this. The brain will kind of move out of your way if you push scissors in. Like this. Go down. Boom. And then I can pull off those pieces. But it all depends on how slow you want to go. The picture of the brain's right here if you want to try and replicate it. We are way out of time. So I'm going to show you how to clean up. Love the cleanup. It's the best cleanup of any messy job you'll ever do. I take all my sharps. I don't know how I got 2 probes. I point them. I stick them into the pad. Take my scissors. I stick them into the pad. Like that. Make sure everything's accounted for. Ruler. All these pieces. I don't know where this. Oh yeah, I had extra gloves. All on there. Ruler on there. Everything's centered. Centered for me. Oh, like this. My big black mat is out here, but I'm centered in the middle. Here's where it gets tricky. You got to remember which side had the seam on the black bag. Like my side is over here. So I'm going to take off my glove that's on the side of that. Oh, sorry. I'm going to take off my glove on the side that does not have the seam. When I took the glove off, I grabbed the outside and pinched it, peeled it off. Hands are nice and clean. A little bit of sweat, but no grossness. Okay. I'm going to switch cameras so I can show you how I'm doing this. And again, you don't have to do this right now if you want to keep dissecting. That's completely up to you. But we dissected what we needed to. So I'm going to point this down a bit. I'm going to roll this out. So my seam is over here. You can see the seam. That's the bottom of the bag. Clean hand, dirty hand. I can touch all I want with this hand. Move it around. But I'm going to always keep my dirty hand on the side with the fish. Clean hand went right underneath, opens the bag. My hand is inside the bag, nice and protected. I'm reaching in. See, reaching back in here. Dirty hand still on the outside of the bag. Clean hand way inside. I grabbed a hold of my fish like I'm wearing a glove, but I'm not. And rolling. Perfect. About halfway done. Take my finger under. If you didn't catch that, put my finger against my wrist and I slid it underneath, wiggled it. Hold it off. Oops. Tuck in the bag. You can take your apron off. You can take your goggles off. Throw them all in the bag. Everything out here now is clean. So I'm just going to roll all this stuff underneath. Somebody else's problem now. Cool. That was fun. I hope you had fun. You should have a bookmark. If you want a copy of the manual that you went through, just reread it again or look at it, just email me. You have a bookmark. On it, it has how you can get some apps. Has how you can download pages from this. Pretty awesome. You can download a picture of a heart, color the heart, take your phone or tablet with the app, look at the heart, and it pops up in 3D, augmented reality. There are video games, like immune system video games, videos on watching blood flow. You can do the same thing with a skull. You can color it. So, a lot of fun, cool stuff. And there are also other STEM things that are in there, like other classes, like the take-home organ dissection. We're working on one for microbes, a video where you can demonstrate how microbes grow at home, stuff like that. But hopefully we'll all be able to come back to places like Jump or the university and we'll be able to dissect together and do all kinds of cool stuff. So thanks again for joining me. Thanks for letting me invade your space and send stinky fish to your home. It's been fun, and hopefully we'll see you all again soon. Bye.